Okay, it's 8:30, so let's start. So we are very happy to hold this tutorial about object localization for free, going beyond self-supervised features and learning. So in this tutorial, we have four different parts. The first one is the introduction of Patrick Pérez, which is entitled Setting the Stage, Visual Objects in Scene Understanding. Then I will introduce you to how to exploit self-supervised features to perform object localization. We'll have a 20 minutes break that coincides, I think, with the coffee break. So there will be opportunities to get coffee then. Then we'll continue with the talk of Thomas Kipf about self-supervised learning integrating object-aware priors, sorry. And the last talk will be by Weidi Xie he will talk about us about discovering objects with multi-modal signals. So we hope you will enjoy the flow of this tutorial. We try to have a story and we'll have closing remarks at 12. So yes, that's for the conclusion. So let's start with Patrick. Okay, so Patrick Pérez is Valeo VP of AI and Scientific Director of Valeo AI. Valeo AI is an AI research lab focused on Valeo automotive application, self-driving cars in particular. Before joining Valeo, Patrick was a researcher at Technicolor, INRIA, and Microsoft Research Cambridge. And his research interests are mainly focused on multimodal scene understanding and computational imaging. So let's start.
Okay, thank you, Oriane. I hope you hear me well in the room, that's for sure, but online to be seen. I'm very happy to be here. So my mission this morning, apart from waking you up a bit with my Father's Day t-shirt, is to give a bit of context for this tutorial. And in particular, I figured that I could try, let's see if it works here, it should work. I should try and elicit a few of the words which are in the title of this tutorial. And maybe a bit to my surprise, it turned out not to be so easy. So in particular, the words object, localization, and self-supervised learning, I'll try to give some context about all of these. And for free and going beyond, I will probably leave that to the few other speakers. So let's go and let's see how we can explain a bit or shed some light on these terms. So what about objects? It sounds obvious, but when you try to dive, it's another story. So being a literary person myself, I turned first to a dictionary. So I went to the online Oxford Dictionary and I asked, what is an object? And so the beginning of the definition is here on the screen, and it says essentially that it's a thing that can be touched or seen and which is alive, which came a bit as a surprise to me, which is from a computer vision perspective, which is not alive, sorry. And so I wasn't completely satisfied. I found it a bit restrictive. So I turned to my other favorite dictionary, which is the Larousse, it's the French dictionary. And I found that the beginning of the definition was a bit more inclusive in a sense. So now it's again about being perceptible by sight and touch, but it's not restricted to not alive things. So otherwise, everything in the room, including carpet, but not you guys and myself, are things, are objects, sorry. So now we are getting closer to what we are aiming at. And also the second one, which I found interesting, the second definition is it's a solid thing made by human to serve a purpose, like a tool. So I found that interesting in the prospect of computer vision. But being a geek as well, and going along with my time, I asked a modern chatbot what is an object. So after a few iterations and a bit of editing, this is the first part of the answer that I got. So in the physical world, an object is something which is, it's an entity which is distinct, which has a place in space and has some properties and can be perceived by senses, so not only sight or touch, which I found interesting. And then I went a bit beyond and asked what what is it for a computer vision person? So for all of us in Vancouver here, and I found it quite interesting that it says that it's an entity or region of interest in an image or video frame, which can be recognized, we'll see, and it can be an object, all or a part of an object like a face or hand for a human body. I think we are better equipped here now. So I'll move to what is a visual object, because we are talking about computer vision really here. And I will propose that an object can be seen essentially as a fragment or region of an image, which stems from an entity. We can call that as well a thing, as opposed to a stuff, which has been also a distinction made in some papers. I'll come back to that later. And this entity, and then we can take different angles to this entity. The first one is a bit conceptual or semantic. In that case, this visual entity depicts an instance of a non-class of object, a non-category, not necessarily existing. So it could be a dog or a dragon, or something geometric, or a very specific type of dog, etc. We can also take another angle, which is physical. In that case, we are back to the definition of the that I was presenting in the previous slide. So it stems from something which is an identifiable structure in the space. It's tangible. It can be live or not. It could be like a stone, something which is made by humans, or it can be defined by the fact that you can use it like something you can sit on, and it's called affordance. You can also think in terms of perception. In that case, the region of interest is so-called salient, because for different reasons, maybe because it stands out in the scene, or it's something that reoccurs across different images or different video frames, or is in front as opposed to the background, or it's unexpected, or it ties with emotions or memories or something which is close to our art. And last but not least, being an engineer as well, you can have a very pragmatic task-centric definition. So it's essentially a region in the image that you need to find in order to serve a downstream task. And this can be dexterous manipulation, it can be autonomous navigation, could be editing a content, or it could be visual search on a search engine. We have many definitions here. So let's have a little detour here. So for instance, to say that again, this is not a very clear-cut definition we have here. So if I show you that, okay, it's a pipe. At least it's the depiction of a pipe, although you might be alerted by the little sentence if you read French, which says this is not a pipe. And if you have a bit of art context or even visual context, like a full picture, then you realize that the pipe is effectively a painting in a museum, which turns out to be a quite famous painting. But this might sound a bit mundane or anecdotal for right now. But if you think in terms of autonomous driving, for instance, and if you have trained a perception system to detect cars or other things, these are real examples of funny or interesting commercials on the side of a bus, but a bit dangerous maybe. And the other one, which is an optical illusion of a 3D zebra crossing, which was, by the way, extremely effective for the human driver to be aware. But I don't know what happens with the robot taxis here. So yeah, we have something to be careful about with the definition. So let's go forward and let's see how visual objects, I will call that visual object or video object in a video, can be now really practically defined for the purpose of the computer vision tasks. So you can start by saying that it's somewhere in the image. So it has a location, it has an extent, and this can be defined by just a center point, could be defined by an axis-aligned bounding box, or the shape of the object, either by labeling the pixels or defining the contour of the object in some way. It can come with different parts or key points, which are arranged especially. So there is a layout, there is a route which says which connects to the global localization in the image, etc. This region can exhibit, or this object, let's call it object again, visual object can exhibit some attributes or properties. Some of those can be transient, like they are temporary, like moving, or the expression of a face can be temporary, or it can be something more permanent, like the identity of the object, or whether it can be used to sit, or it has certain colors, at least it can be permanent for or persistent long enough in a video, as opposed to a very transient thing. Another aspect, which is more multimodal, this object can emit sounds. So we'll come back to that at the end, and also in other parts of the tutorial. And last but not least, it can relate to actual semantic categories or subcategories. It can be coarse category like a dog, or something very specific like like husky, very specific breed of dog, etc. And what we will focus mostly on today is what is called localization. So I get to the second term I wanted to elicit in the title, which is localization at large with different meanings, as it were. Okay, a few examples to illustrate what I was saying. So in this urban scene, so you might be after detecting pedestrians. So in this case, it's axis-aligned bounding boxes around the pedestrians. And then in particular, if you want to track them, you want to give them IDs. So here comes different colors for the different pedestrians. But if you are more into analysis of each of them, you might go after different attributes. In this work, we in collaboration with the PFL, we looked at a large number of attributes, including the age, the garment, the intention of the pedestrian to cross, for instance, or the attention of the awareness of the car, which are obviously very important to look at for safety reasons. A similar thing on the video now, where we have these important attributes of intention to cross or holding a mobile phone, but also you see the pose in 2D, which are the joints, which, by the way, in terms of object, a joint is not a visible object when you think about it, especially if you ask the annotator to do the annotation. The joint is inside the body, and then most of the time the body is covered by cloth, so effectively it's not visible in the image. So again, to make the point that objects, even visual objects, are not always that easy to define. Another example from an old project of mine back at Technicolor, where we wanted to annotate all the faces in one Woody Allen movie, and Hannah and her sisters. And what you see is the head. And I remember trying to specify the task for the annotators. So is it the bounding box? What do we do with things which are occluded, etc., etc. On top of that, also on this example, we annotated not only that there is a face, but who is the character, who is the actor, and if the person is talking or not. That was quite fun, actually, and it's a very good movie. Okay, so objects. Visual objects very important to understand scenes, and they, not surprisingly, come along or are at the center of a large number of tasks. And I will try to give sort of an overview of these tasks. And this is not going to be exhaustive, but I hope it helps mapping a bit the different categories of tasks. So the first class of tasks that I would like to highlight, and actually they are at the heart of the tutorial, is when you are interested in arbitrary objects. Okay, so they can be essentially anything, and the core of looking at this, the core of the tasks is about matching different views or different views of this arbitrary object across images, etc. And so either different views of the same object or different instances of the same category of object, even if you don't know what is this category, it can be unnamed. Okay, and you can do that. We used to do that with very low-level features, colors, etc., all the way now to deep features, and this can suffice. You can do that online, even in a video, or you can do that offline in a collection of images, and it's called transductive setting. And so essentially what I'm saying is that there is not much semantic here, but there could be a bit beforehand because you are using features which have been learned in a supervised fashion, or you, as we will see, you can use a trained object proposal, which have been trained on actual objects. And now coming to the actual tasks themselves, or at least the one which are quite popular or at least recognized. First one is the unsupervised object discovery at the category level. You can also try and discover objects in single images, and we will see much of that later. You can try and retrieve an object from different views. You can try and recognize that this object in this camera it turns out to be the same reappearing in another camera if you are in a, say, in a surveillance setting. It's called re-identification. Related to that, you might want to follow an object across the frames of a video or of multiple videos. It's visual object tracking typically with bounding boxes, not necessarily, but typically. Or you can try to delineate precisely this object through time. It is called video object segmentation. Okay. But you might also be really interested in a specific catalog or taxonomy of objects. So in that case, obviously, you need semantic supervision if you do that with machine learning. The three typical tasks are object detection, meaning implicitly at the category level, instance segmentation, so segmenting a specific instance of specific categories, and multi-object tracking, where you want to track through times instances from your catalog of classes. And I will show examples in a minute. And of course, things are moving fast in the community, and now you have all the what you can do with free-form or text-based analysis, where and it goes beyond objects here. It's really about scene understanding at large, but with objects being important there, trying to understand in an open way scenes using pre-trained visual language models. And there is here a few tasks which are sort of prototypical, doing zero-shot detection of objects or segmentation, captioning specific part of an image, visual grounding, which is to localize text, or referring expression segmentation, which is the similar task where, given a descriptive text, you want to segment the part of the image which corresponds to this description. And going forward, you might want to answer visual questions about your visual scenes, etc., etc. So as I said, or maybe one way to simplify this map here is to say that the first one block I mentioned, there is no such as a vocabulary. In the one on the top right, it's a closed vocabulary or closed set, and now we are opening up in the third part, this third block with open world or open vocabulary. There are different terminology at the moment. Okay. So I say a few words about, because it won't be discussed much in the rest of the tutorial, about going after objects from non-class. So as again, you need supervision here because it's semantic, but the supervision can come in different forms. It can be full supervision, where you have, if it's for detection, where you have the actual localization of the as ground truth of the objects, or you might have only image labels, so you don't know where it is, so it's weak supervision. And if you train an object-centric task with non-categories, it might be because it's your actual task of interest, or you might do that in order to pre-train a representation that you will use later for other tasks or other classes in the case of zero-shot or few-shot learning. So again, the three key tasks here are detection, segmentation, and tracking. So detection and tracking, in a sense, they are, detection and segmentation, they are very close in one, very much related. In one case, you are typically after a box, and segmentation is you are after a precise delineation of the object. The classic data sets are Pascal visual object categories, Pascal VOC, or Microsoft COCO, which stands for Common Object in Context. And you have the classic metrics around the average precision, or around the intersection over union IOU. And here are some popular tools like RCNN for detection and mask RCNN for the segmentation part, and for detection either a single stage detection SSD and YOLO, and then the start with the transformer with deter in 2022, I think, or 21. And you have lots of very good resources online, in particular the library Detectron of Meta, or this open MMLab resource where you have specific libraries, one for detection, one for segmentation. And likewise for tracking, it's been a very long-standing task. So you have a long history of test beds, in particular the multi-object tracking mode challenges in 15, etc., all the way to 20. For the metrics, it's a bit trickier. So you have all the detection-based metrics, but then you want also to reason at the track level. So you have track specific metrics, including the one which is about identity switch. You might be, I mean, it's quite common when you have crowded scene of some same category object that you exchange identity, and this is not good. So you have to put that in the metrics, etc. So again, a few, it's very partial, and of course, a few recent good trackers that I put on the slide, including some with transformers. And again, in the OpenMMLab library, you have a library for tracking. Okay, so this is for people playing with detections, they know this, but this is just to illustrate Pascal Vogt. And here you see that you have all the boxes, and they are really bounding boxes in the sense that the all object is included in the box, and you have additional things like saying what is the orientation, well, in a crude way, or also whether the object is partially occluded. So you have additional attributes associated to this box in addition to the location and the class. And if you go to instance segmentation, this is the MS Coco example. And actually, there is a nice tool to explore this data set. So you can specify, for instance, that you want to, so in this case, there are 80 classes. Pascal Vogt is, I think, 20. You can specify that you want a scene with pedestrians, cyclists, all the road users you might imagine, and also signs. And actually, I found these two scenes in the data set with the segmentation, and you see that it's fairly detailed, and probably it has been a nightmare for the annotators. And you can even do that in videos. And yesterday it was mentioned in a workshop. For instance, in the Waymo Open data set, there is a semantic segmentation, instance segmentation video instance segmentation challenge, and this is one example of the ground truth. And effectively, each pedestrian is individually labeled. I don't think it's very visible on my animated GIF. Sorry. Okay. Just a word on, of course, I'm not going to dive into these graphics, but just to say that, first of all, that if you don't know yet papers with code, it's a fantastic resource when it comes to benchmarks, state-of-the-art performance, etc. And this is to show you within 7 years since fast RCNN, the progress in object detection on Coco here. There is still some room, but it goes fast. And the same for semantic segmentation on Coco as well, since 16. So maybe after this CVPR, you might try and fight for these competitions. All right, tracking, multi-object tracking. So these are two examples, one old, one recent. The recent one shows a very crowded scene where you have a multi-object tracker for people. So it's really about detecting and tracking people. So in that case, it's a mix of detecting things, objects, and matching them across time. So it's about alignment. And this is done with a transformer in this case. And what you see at the bottom, I like this old example of tracking mice. So again, it's a non-category. So there is a prior on the shape of of a mouse. So there is a parametric shape model which is used, and you see here it's tracked. And at that time, it was done, I think, with a particle filter of some sort. All right. Okay. Now I'd like to switch, and we're getting closer to the core of the tutorial about arbitrary objects. So one task is given a single scene, a single image to find and even segment things which are interesting for one reason or another. And actually, it's like all the tasks I just illustrated before. It's not a very recent problem. And I like this example of GrabCut, which is about foreground subtraction using simple color modeling. By the way, for the people who have PowerPoint on, I think it's at least on Windows, you still have in PowerPoint this remove background feature for images, which is super. I used it for this presentation on PowerPoint, and it's based on this work from Rother et al. In 2004. And but now we do that in a more powerful way, and Oriane will talk about it using pre-trained self-supervised features, essentially to find salient objects in a single scene. But you might want to do also to find arbitrary objects across images. So in a sense, you match one view to a collection. It's one-to-one matching. I'm going to show an example. And it's typically, I'll show examples. And also you might want to do that collectively in a collection. So it's essentially end-to-end matching, and it's grouping or clustering. You call it the way you prefer, and I show an example. Okay, so another old paper I love, which is by Sivic and Sisterman, Video Google. So and there was a demo online. I don't know if it's still online. So you can take one frame from a movie. In this case, it's Groundhog Day, and you select by hand the tie of an object. So it does the tie of Bill Murray in this case, and then you can retrieve it all across the movie. It turns out that he has the same tie in a few scenes, and you see that even on the top right, it's a true positive, and it's only based on local features, what we now call engineered features. And you can do even more because your selection is a video frame in a movie. You can start by tracking the nearby frames in the same shot. So you have then you get multiple views of your query. It's query expansion, and then equipped with these multiple views, you can have an even better retrieval in the rest of the movie. And these are examples that are retrieved, and some of them are pretty difficult. I don't know if people see my mouse here, but you see that the van here is at the back in the scene, so it's been retrieved. So very powerful, very neat work. Similar thing with tracking. So here it's about tracking a completely arbitrary object. On the left, what you see, going to loop now, you will see that there is first a selection of the face. So the guy who turns out to be the author, Kalal, is essentially saying, track my face. Okay, and then there is a little game with a photo collection where there is his face, but essentially there is no the algorithm is really about finding different views of this very same object, which happens to be the face of this guy. On the right, you see similar things just based on color. And in this case, you see also that it's not necessarily a bounding box, but it could be an ellipse in this case, so you have more degrees of freedom. But there is no semantic knowledge whatsoever here. And now if we go to segmentation of the object. So this is an illustration of a task that is usually called visual object segmentation. So you select an object in one frame or in several frames, and you want to segment it all over the video sequence. In the context of video editing, it's called cutout. Sorry, there is a typo. I see now. But also, if you are into the movie industry, it's called rotoscoping. It's something very useful for visual effects. And you see here something from 15 called jump cut, where I think they have not been reloaded, the slides. Okay, doesn't matter. And you see that the objects can be very complex, very flexible. There is a ball, there is the guy, and again, there is absolutely no semantic prior here involved. It's about local appearance modeling and matching things through time. Okay, how am I with time?
5 more minutes.
5 more minutes, that's good. So one thing which proved quite interesting in the object the detection community, in particular with faster CNN, for instance, is the idea that you can in order to detect objects from non-categories, you might start by trying to detect or to propose regions in order to speed up things, to propose potentially interesting regions in your image, which are likely to contain an object. And this is, it's called region proposal, object proposal, and they come with a degree of objectness, and it's something which is very convenient or very useful, and there are different flavors of that. So one, for instance, with selective search in 13 or edge boxes in 14, where it's based on extremely low-level features, no real training here, either for selective search based on superpixels or fragments which are aggregated at different scales and aspect ratio, and you end up with a few hundreds, a few thousands, sometimes proposals, which can be then processed by your detector, which is essentially then a classifier. And the same with edge boxes. In that case, you are looking at the strength and orientation of the edges in some regions of the image. But you can have more powerful things, in particular, as I said, with a faster RCNN, where effectively the box proposal thing is part of the network, so it's trained actually with semantic supervision, because you rely on the object ground truth here, and so it's called RPN for region proposal network. Okay. So, and you might, using this thing, you can detect, you can do what is called unsupervised object detection or discovery, sorry, where given across a collection of images, all these region proposals, and you characterize them in terms of saliency and also pairwise similarity, you can find, you can build a graph, or you can discover a graph with some either heuristics or more sound methods, and you see the key references here in order to discover, as in this example, that some images share common objects in this case at the category level. And this is just examples where you see that you can discover planes without knowing what is a plane, or you can discover bicycles, etc. And at the bottom you see examples, results in images compared to the ground truth in the ground truth is in yellow. So on the right, you see failures. So I'll go, I'll skip that now, and I'm almost there. So what I've just mentioned here is the idea that we can start discovering things, in this case, in the previous case, at the category level, but without any semantic supervision, so no class labels. And so that's good. So which brings us to the other talks of the day. But just to, in terms of terminology, one quick point here. So I know it's not always frozen, but effectively, there is something which used to be called unsupervised learning, which is about discovering without supervision at all structures like clusters, low dimensional or low rank structures in your data collection. And you have all the usual suspects in terms of methods here. And then there is self-supervised learning, which is more about setting up a pretext task. So there is an actual task that you build yourself, for which the supervision comes for free from the data, and then you supervise the learning of the representation for this task before, and then hopefully the representation is useful for other tasks. But in a sense, at least in many cases, there is some, at the end of the day, there is some kind of underground supervision here, which already starts with the selection of the training data, at least when it's not at a huge scale. You select the data. For instance, if ImageNet, it's object-centric images, etc. They are vertically oriented, so the gravity goes this way. It sounds like mundane again, but it's something. It's a choice. Okay. So self-supervised learning, there will be more of that in the other talks. So there are classic pretext tasks that you can play with. Either you try to recover things that you have hidden, could be the color, it could be part of the image, could be the next frame in the video, etc. You might want to recognize transform that you have applied to the object, like rotations with RotNet, and you apply the transform, and you want the system to recognize this transform. You might want to find groups which are meaningful, typically deep clustering, or something very powerful which is to apply different transforms which don't change the semantic of your image, and then you want to find representations for which are invariant to these view changes. And also, if you have multiple modalities, you might align across the different modalities. And in particular, this view invariance, missing something. And depending on what you do, you have different learning techniques, different losses, can be generative, discriminative, contrastive, or using distillation, and it's called self-teaching in this case. And just to, and I'm not going to explain that, of course, as well, but just to show the variety of things that people have come up with for self-supervised learning with view invariance. Some of them where there is EMA, which is exponential moving average, means that there is a self-teaching going on here. See, some of these things are pretty famous, Dino in particular, which will come back in the talks. All right, looking forward, and that will be the end. So I was really focusing on images here in my presentation, but obviously, and we see that at CVPR, computer vision people are not only about after images, they look in point clouds, videos, etc. So other signals for people doing autonomous driving, like we do at Valeo.ai, we are very much into bird eye view, which is the top view above the ego car. And of course, in this example from Agroverse, which I saw yesterday, you have everything represented. So the top view, the fact that you have two modalities, the LiDAR and the camera, and you're after objects, the non-objects, the cars, but it turns out that for autonomous driving, there is a very long tail, and there are very rare objects that you might want to accommodate with open vocabulary. Which brings me to this. So there are plenty of things going on now, new architectures with the visual transformers, the slot attention that we will be discussed at length by Thomas. And of course, there are all the promises of these foundation models and generative models in particular, but visual language models to do reasoning, to revisit all our few shot and zero shot tasks in a much more powerful way. And to finish with links to what is going to be be presented now. Oriane will talk in particular about the use of self-supervised representations. Thomas not only, but also will talk about slot attention, and Weidi will tell us a bit more about multimodality and also, I think, the use of visual language models. And with that, I will stop. Thank you very much.
Time for one question.
No questions? Okay.
Maybe,
no question?
maybe I
you have a question?
I have a question.
She has a question.
You define a lot the objects and so how they are, and I was wondering.
This is not prepared.
I was wondering how does the definition of the object impact what we do afterwards? And I guess it changes to be on the task, etc. But do a better definition will help us think. Do better algorithms.
I think at least okay. So at the end of the day, you need, because we are solving tasks, I guess, at the end of the day. And even if we do self-supervised, we need ground truth for at least to compute the performance. And in order to explain to the annotator what to do, I think you need to be extra careful. And I think, and it's probably one thing I've seen as an evolution in the computer vision community through the 3 last decades, it's very much driven by benchmarks now, which is good. It really helps pushing the envelope, but the benchmark defines the task. So, which means that the ground truth define whatever you do. So you have to be, and if you are solving a task which is not, it might be good for only academic work, but then if you want to deploy on the real world systems, you'd better make sure that the task is really well aligned. So meaning the annotation well aligned with your final task. And we see that every day when we work on driving automation and driving assistance. Thank you.
Thanks. Okay, so I have the honor to introduce myself. So my name is Oriane Siméoni. I'm a research scientist at Valeo.ai. I've done my PhD at INRIA Rennes before that. And I will talk to you today about how to exploit self-supervised features in order to do unsupervised object localization. So Patrick mentioned that object localization is a key problem for many systems that we have today, either on the object. So you can define in different ways. You can think of it as object detection. So you want a box where you have your object. You might want to label each pixel, knowing exactly where are the objects, and you might want to define the instance to separate each object. But in order to produce good quality models that will do those tasks, you will require a lot of annotation, human-made most of the time. And you might also need to define a finite set of classes. And we are seeing it now, a finite set of classes, finite vocabulary is quite restrictive. And with VLMs, with Clip, etc., we want more open world solutions. So in this talk, I will talk to you about how to perform object localizations with no annotation. And in particular, that might help for instance, discovering those types of objects. And you might also think of Segment Anything, which was produced in early this year, which has shown the interest for the entire community to segment things, no matter what their class is. We want to find the objects. So let's start with this image that I'm sorry you will see a lot during my talk. So there are different tasks when we consider unsupervised object localization. The first one that has been defined by Patrick earlier today is unsupervised object discovery, where you try to find one object. You know that every image contains at least one object, so that's it. You want to fit a box to at least one object in the image. The metric to evaluate this is called correlate, and it's basically the percentage of correct boxes. So you compare each box to ground truths, to all the ground truths that you have, and you find the one that are correct. And so with that, you have a pretty good idea of, is my one box correct? Another task is unsupervised saliency detection, where this time you want to segment a foreground mask. So it's one mask per image. This is evaluated with IOU or accuracy. And here again, you don't do discrimination between objects. You just want one foreground mask per image. So this is single object mask tasks, but the community has been working quite hard on this unsupervised object localization, and now methods are tackling multi-object problems, where this time you might want to detect all of the objects in the image, sorry. And so you can do unsupervised class agnostic object detection. And the other side of it is unsupervised class agnostic instance segmentation, where this time you have one mask per object. So we'll see through my talk the different methods for both of those problems. So some background. So Patrick mentioned before CNNs were very successful, before transformers, obviously, they were handcrafted features that have been very useful and are still actually actively used right now. Selective search and edge boxes are two methods that allow to use the pixel level information and to produce a lot of boxes. The recall is really high. You know that most likely your object is one of those boxes. But the precision is low. What is a box that you want to focus on? What is object, what is not? On the other side, you have methods that have tried to think of the object discovery problem as I have a data set. I know in my data set I have recurring patterns, recurring objects, and I want to find them. So the idea there is that you have probably proposals in your image, and you might want to match all of your proposals with all of the one data set and try to find the one that are repeating a lot, the popular boxes. So this is very interesting work. However, it has quadratic costs. You need to compare all the boxes to all the boxes of the entire data set. So it's not really scalable. Okay, so that's for some background. Now, what happened in the last years is that self-supervision appeared to be very, very successful in doing image representation with no annotation. You might think of RotNet, which I guess is easy to explain, is a self-supervised learning task where you are just trying to predict, is my image, by what angle, sorry, is my image rotated? So by this very simple task, you're able to learn image representations that you can later use for fine-tuning, for unsupervised methods. So pretty interesting. So there have been obviously more complex objectives, like in deep cluster, that have been produced, and the literature for self-supervision is very big at the moment. So another thing that happened is that transformers, became a thing for vision. So with VIT being published in 2020. And that was very interesting because suddenly you are not just looking with CNNs, we were looking at local information. So the pixel around my pixel. And so you have information about what is happening around the pixel of interest. But with transformers, now you can attend, every patch can attend to any patch in the image. So you can correlate things that are far away in the image. And that was very interesting for context purposes and for just thinking of the problem a bit differently. But transformers were great or are great, but I have a problem that they are quite hard to train. So you need either a very big data set, millions of images that have been labeled, or there have been solutions recently of trying to help with the training by doing pre-training learning using self-supervised objectives. So MoCo, Dino, and MAE are just a selection in those latest. And here again, the literature is very big. And every time you have a different objective, but the idea is the same, you have a proxy task as you try to define the best to learn a good representation. So in this talk, I will talk a lot about Dino, which has shown to have very good localization properties. So just Dino, how it's trained, you have one image, you have two crops of this one image, and basically you have a student and teacher model that are trying to predict the same classes for those two different crops. The teacher is a moving average of the student, and that's it. So that's a very simple objective. And it was very interesting because if you can see at the bottom, when you have a point on your bottle, like on the left, top left here, the red point, you can see the attention map of that point with regards to all of the other patches. And you can see that all of the bottles are appearing. They are localized. So when we saw this, so obviously Dino highlighted that in the paper, the authors, Karen et al. Highlighted that in the paper. So the localization properties are really interesting. There was this one work as well that is pretty interesting, that is deep bit features as dense visual descriptors. And what they did here is that they took Dino and they observed the patch features in, so here is a TSNE visualization, and they compared it to a supervised VIT. So it's supervised with classification task. But if you look at the feature space, in the supervised setup, you have patches that are grouped by classes. So you can see that you have subgraphs that are basically different classes in data sets. But when you look on the left-hand side, you can see in the graph or in the feature space that your patches are localized by type of patches. So torso are on the bottom right. You have the legs on the bottom left. So that's very interesting. Dino indeed is really including a lot of information. So in this presentation, I will talk to you about how to exploit the self-supervised features to produce object mask in the first part. Then we will talk about how to improve those predictions using learning. And finally, can we go from class agnostic to class aware? What are the solutions? So let's start. Sorry. So if you look at Dino paper, this is the first figure. And so when I looked at it, I was like, okay, localization is done, right? So you have your bird is very well localized. You have your toothbrush is very well localized. So this is the self-attention map of the last layer of the transformer. And so I was very impressed with those results. Obviously, there is a bit more to it. So those self-attention map are produced by using the keys and queries features in the last attention layer. And what you can see here is one selected attention map in the different heads. So the way the multi-attention head is working is that you have several heads. And here they basically cherry-picked, or they picked some visualization for the images. And so if we look at actually more complex images with more objects and maybe yes, just more different scenes. Then if you look at the different heads, the attention, it's not obvious where it's looking at. So if you look at the top row, it's mainly focusing on the car, but where on the car, we don't really know. Sometimes it's quite noisy. On the bottom row, it's sometimes focusing on the person and on the dog. And so looking at different heads, looking at this, it was hard to know how to exploit this directly. Instead, what we did was to look at the key queries and value features that are interesting, that are producing those self-attention map. And by doing so, we do not require to make any decision on the heads. What we observed is that the keys in particular have a very good correlation properties, and that the features for the object patches are more discriminative than the one for the background patches. And that's one thing that we observed that we are going to use a lot during this presentation. Basically, the features for the object have more to it than the one for the background, which are more uniform. So object patches are less correlated to other patches than background patches. So most of the methods that we're going to see now are requiring a graph of patches features. So how do we build this one? So we have our image, which is cut into n patches. It's going through a frozen self-supervised backbone. At the end, we have our feature tensor. We are here looking at the feature space. So obviously, it's a very high dimensional space, but I represented it with only three axes. But imagine it in a much larger scale. Okay, and what we do then is that we consider every node, and every node is becoming, every patch is becoming a node of our graph. The edges are the cosine similarity, which is a dot product between the descriptor for each patch. So each node is compared to all of the other patches. And then we connect patches that only have positive cosine similarity, so that are correlated. We don't care about patches that are decorrelated. Okay, so doing so, we are able to have our graph, which is not fully connected, it's partially connected. It's binary, so we are just going to say 1 or 0 on the edges. And for visualization purposes, for the rest of the presentation, I will not have the edges represented, but keep in mind that they are here. Okay, so when we look at our graph, we can see really distinctively 3 different parts, and that's what we are going to try and find with our methods. So the first one is one that we propose at BMVC 2021, so just following Gino, where we use 2 assumptions. The first one is that foreground patches are less correlated than background patches. So that was the idea I told you just before. And that there are less patches of objects than background in the image. So that's quite a strong hypothesis that is discutable, but it works for most data sets that we are currently using. So we use a very simple concept. We use the information of degree. What is a degree? The degree of a vertex is a number of edges that are connected to the node. So here you have a degree 2 and 5 on those 2 patches. And so we compute the degree for every node. And what we observe, so in the background, the patches have a higher degree than for when they are on the object. So we use exactly that to set the object seed as the patch with least lowest degree, the patch the least connected. So that was, for instance, here focusing on the head, that works quite well. And then what we did was to select the similar patches to this one, and then to further extend the regions to those similar patches. The further extension was important to have the entire object, otherwise we will just get a part of it. Okay, so the benefit of this method is that it's very quick, very easy. The computation is 60 frames per second on a single GPU, so very quick to compute. We achieved significantly better results than inter-images methods that have this quadratic cost. But in terms of limit here, we are only talking about single object detection. We have issues when objects cover most of the image. Okay, and we are achieving a coarse mask. So it's not the best mask that you have ever seen. Then following LOST, there was token cuts that was introduced at CVPR23 that used an assumption quite similar to ours, which is that foreground objects can be segmented into self-similar regions. And using this assumption, they used the normalized graph cut problem, which is simply as following. You want to cut your graph into two sets of graph. So you want to do a bipartition where you have the minimum similarity between your two sets and the maximum intra-similarity within your two sets. So they solve this so you might search for different solution, and that would be, for instance, an optimal solution. So they solve this way using spectral clustering, so using the first eigenvector. I invite you to go to the paper. It's well described how they do it, and it's a nice read. And now, given this bipartition, we want to know what is the object. So obviously, we want to detect the partition corresponding to the object. And what they propose is that you basically select the patch with the least connection again, and the set that includes this patch is the object. And so they achieved good result as well. In terms of benefit, we have with token cut a more refined localization. The masks are better. We are still obviously better than inter-images methods, and they also have shown quite interesting generalization property to different features. So we had studied things only on Dino, and they show that it can work on Moco and other self-supervised features. In terms of limits, so they are still single object detection, and they require to compute eigenvector. So it's a bit slower than what we had before. A very related work is deep spectral methods that was published also at CVPR 2022 last year, where additionally in their graph, they employed handcrafted features, so they use some pixel level information. CVPR 2022 was quite a big year for unsupervised object localization. Okay. And one extension of token cut is published this year at CVPR is mask cut, where the idea, so it's in the Cutler paper, and mask cut idea is that token cut is great, and it feels like you could discover more than one object. And how they propose to do that is so you have your bipartition that you had before, you have your set of patches that are the object, and what you can do is you remove it from the graph, and then you go again. You compute your bipartition again and again, and they do it 3 times. So there is a bit here, the assumption that you have more than one object in your image. They have some heuristic to say this is maybe not an object. The heuristic that they are using is object-centric prior, where the idea is that the foreground set contains less than 2 of the 4 corners. So it's quite handcrafted heuristic, but anyway, it works enough. And so in terms of benefits, here they are doing several object localizations, so that's very interesting. They also have the good quality of localization that token cut has. But in terms of limits, we can ask, are all of those detected objects really objects? And they require to compute eigenvector a few times in an iterative process. Okay. Still CVPR 2022 last year is self-mask, which I find interesting because, sorry. Oh, okay. I find interesting because they show that you can use different self-supervised features, that they all have their own properties that they will localize more certain objects or more certain other objects. And here what they propose is you have different features, pre-trained methods, pre-trained models, sorry. For each of them, you apply spectral clustering, you find your bipartitions. And then you can, with a simple voting scheme, find the one that is the most popular. So they do that and they obtain a good mask at the end. So in terms of benefits, they leverage several self-supervised features. So that's interesting. In terms of limits, you need to do forward pass into different models that has some cost, and you still need to compute eigenvector, which still has some cost. And this was a single object detection. Free mask is slightly different because they are at that point just using the attention. So they are using the assumption that you might not need, so you might use the attention mechanism, which is well defined to, given a certain query, find what is matching in the keys. And so what they propose to do is to consider every query patch, to compare them to every keys, and to obtain the number of queries patches, they obtain that number of masks. And then what they propose is to sort those masks and to use an NMS-like solution to filter out the masks that they don't want, that are repeating and that are overlapping. Doing so is pretty interesting because they are able to highlight several objects. We are here getting closer to the instance. They're able to produce a mask per object. And so in terms of limits, however, they have some noise. The mask, again, it's hard to know what is the object or not. And they have, they propose a type of objectness computation, but that is not that clear. You have no annotation here, so it's very hard to define. So it's hard to filter out the bad mask in their method. But it's producing already pretty good results. A final work that is just using features as they are is found. So found we're presenting it this year at CVPR23. And here we're just thinking the problems the other way around. So people are trying to find objects, but then it means that you need to know how many objects there are, what type of object. You need to have some priors about they shouldn't be more than 2 edges of the image, which is quite limiting. And so here we just thought, okay, what about just if we were looking for the background instead of the object? And doing so, basically, we are able to highlight what is not background, which by definition will be object. And so we use a very simple assumption, which is a background receives little attention in the self-supervised features. So we take our attention maps, we find our background seed, which is a patch with least attention, and then we find what is matching to the background seed, and that's it. We got our foreground. So that's very, very quick to compute. It highlights several objects, but in terms of limits, there is no clear instance. We don't separate the object, and the masks are quite coarse. But we'll see later that through training, we can really use that. So some result now. How does this method work? So you have on the right results visualization for this I took from token cut paper, where you can see lost and token cut, and you can see that they are able to detect objects, actually detect different objects. One is going for the tree, one is going for the person on the top image, but the detection are pretty good. You also have here at the bottom 3 mask outputs, so you can see that they have a mask per object, although the mask is quite coarse. And in terms of quantitative results, what we found pretty interesting is that on VOC 07, 12, and COCO, basically we achieved 70% of quality. So 70% of the masks are good. And that's quite high for a non-supervised method. On COCO, it's 60, and COCO is known to be harder. You have lots of small objects. It's quite difficult. So those results are pretty impressive for a method that requires no training and that just exploits something that has been trained by somebody else to do a task that is different. So there are also simple ways to refine the predictions that are using pixel level information. And those are bilateral solver and conditional random field that you can apply directly. They require no training. And they're allowed to go from, a coarse mask that you can see in the middle, because you are limited by the patch resolution, right? A patch is between 8 and 16 pixels, so that's quite large. And by using bilateral solver here, they're able to produce this very fine looking mask that is really highlighting, I think we can see the dog hair. So it's pretty impressive. In terms of limits, it's post-processing, so it has some costs in terms of speed. So takeaway for this first part is that it's possible to discover objects with no annotation by using those self-supervised features. It's easy to discover a single object. It's harder to go to several. And we got interesting performances on VOC and COCO. What remains to be seen is how to go for a successful multi-object detection, how to exchange information at the dataset level. We have those datasets, they are here, we know they are repeating objects, how to use that. And so in general, how to refine results. So let's now go to the second part, which is improving through learning. And in this part, I'm going to talk to you about just the idea that, so you have your images, your data set. Sorry, I was too lazy. I put 3 times the same one, but imagine different images. And for each of those images, you produce pseudo labels, which will be coarse masks. And the assumption is that with training, we can go from single object discovery to multiple object localization, and that training will help with smoothing out mistakes. And so what many methods have proposed is to train a model by using those pseudo labels as pseudo ground truths to train the model that you want to produce. And you might want, for instance, an object detection model. So you might put, instead of object detection model, you can put FASTER or CNN or your favorite object detector, and use the pseudo labels as ground truths. And here what you simply do is that you had a mask and you just fit a mask to the biggest, to the largest connected component in your mask. You just fit, a box, sorry. And by doing training, you can go to multi-object detection and you also achieve better boxes. So we had proposed in LOST to use a class agnostic detector, which was in our case FASTER or CNN. We didn't do anything to it. We just took out of the shelf. And we were really impressed by the result that allowed for us to reach those types of detection that you have on the bottom left, where you have multi-objects in your image detected. And in terms of results, quantifiable results, if you look at loss and token cut plus CAD, you are between +3 and +7 points. Just by training a model to do so. The better results, the most impressive results are on Coco, obviously, where it's harder. And so basically, it's pretty interesting to see that with a simple scheme, with just training a detector, it will have only 1 box per image during training, but it still is able to regularize. And so your boxes are better, and it's also able to find more objects in your image. If you are this time interested into foreground segmentation, so you just want the object, 1 single mask per object, there are some works. So the first one is self-mask. So we've discussed before about how they produced the coarse mask with the different self-supervised features. And here what they propose is to learn an encoder-decoder architecture, to produce mask at a higher resolution. And they have shown that by learning, they are really having a great boost. I think it's +14, 16 points. So it's very impressive. And in terms of architecture, again, they didn't do anything very particular. They just use a mask former, which has an image encoder, a pixel decoder, and a transformer decoder, where you have queries that you will learn through training. And then you learn to score those queries based on your pseudo ground truths. So they achieved really good results, and they have been used subsequently by other works as well, because the training is quite smooth. So I talked to you before about found, how we discover by using the background, the objects. And what we did, it was a very simple idea. I was thinking, why do we need to train a very big detector, segmenter? Dino is already having all of the information we need. So why not just having a single conv11? So we propose to train a model which is a conv11, which role is to say, is this foreground or background? That's it. And we used to train it to the pseudo label mask that we achieved before. And by doing so, with a 2-hour training, on a single GPU with no annotation, we were able to achieve state-of-the-art results. The inference runs at 80 frames per second. So obviously here we are not talking about instances, we are not really separating the object, but we are really highlighting all of the objects in the image. So we were quite happy with the results. Another work I would like to highlight, which is MOVE, that it was presented at NeurIPS last year, They are doing something a bit different. They are thinking about with the concept of if you have a good mask, you can remove what is in the mask, you inpaint with some background pixels what was before the mask. And then if you paste again your mask somewhere else in the image, a discriminator shouldn't be able to see that that's a fake image. So they train this way a discriminator to say is it fake or not. And by doing so, they achieve pretty good results. Their mask producer is just a segmental model, which is a VIT. I think they tried Dino and MAE, plus a CNN head that generates object mask. And then they have this discriminator that say yes or no, it is fake or true. And they achieve, yeah, good results. There was also a redo that was presented at NeurIPS 2019, which is on a similar idea. This time they were using a GAN-based method with a pretty similar concept. Okay, so now we have seen how we can do foreground segmentation, but what about if we want instances, we want to separate objects? There has been two works that I would like to highlight here. So Free Solo was last year's CVPR, and what they propose is that we've seen their free mask that they generate just using the attention. And then they proposed to train a solo model, which was one of their prior work, that is going to do instance segmentation. But they observed few things, that during training, the training was not really smooth. And so they reduced the loss from a fully supervised loss to a weakly supervised loss, where they are not going to train with a mask level annotation, but with box. So they are just fitting a box to the masks that they have, and they try and force the model to learn the good mask with those box level annotation. They also added a pairwise affinity loss, which is working with the idea that two close pixels should have a same class. And so with those just few tweaks, they were able to achieve good training and to obtain results that you can see here, which I find quite pretty. So that was really good. And an update on Free Solo is Cutler, which is presented this year at CVPR. As I was saying before. And here again, they are taking off the shelf Mascar CNN, Cascade Mascar CNN that are doing instance segmentation. And they have a few tricks to make it work. The first one is that they will drop the loss for predicted regions, that are matching any pseudomask. Doing so, they don't want to handle the noise that you have in the pseudomask, because you don't want to force every pixel to be exactly like the coarse mask are, because it might be a bit noisy. So that's helpful with that. They also have a copy pasting augmentation scheme that help them with having more data, basically. And they also propose something which is, I guess, quite simple to think of, but works quite well and has interesting properties. They propose to train several times. So they do a first training. Now they are able to achieve multi-object discovery, multi-instance segmentation, and they have better results. So then they take those predictions, they take the better ones, and they are going to go again with training. And they do that 3 times. And what they have shown is that by retraining again and again with better and better pseudo labels, what happens is that you're able to find more objects. And so this is what you can see here, where in round 2 and 3, you are able to achieve up to 3 million instances versus 2.5 in the first round. So pretty nice. So that's it for the training part. So what we've seen is that with training, you can boost really the performances, and you can regularize any mistakes that you were doing before. You can also go from single to multi-object detection, localization. But now the question are how to further improve results. You are also limited by the abilities of the self-supervised features. So you are constrained by them because you're not doing any retraining. Every time those features were frozen. And also, what about classes? So, okay, so we've seen that. So let's go to class aware. What can we do? I will not go into much detail here. Oh yes, sorry, I forgot. Okay, so the methods are all using Dino, which is trained on ImageNet. ImageNet, we all know it. It's quite curated. Somebody can argue. So it's maybe some type of supervision there, but it has a very constrained domain. And we've found, and Tokacut also shows that you can really go to out-of-domain images, and you can detect things that are cartoons, that are objects that are unexisting in the world or will never be seen in ImageNet. And so the properties are pretty interesting. So we find really objects without knowing what without having strong constraints about what an object is. But now if we want to assign a class to those masks, there are two solutions that are quite straightforward. The first one is considering closed vocabulary. So you already know the set of classes you are interested in. You are in the VOC or COCO 2080 classes. And what you can do is take your mask. For each mask, you take a descriptor with Dino. You put that into your feature space. You apply k-means. You define k as a hyperparameter. Unfortunately, you cannot really avoid it. And then you find your clusters in your graph, and you are able to assign each mask a class. So that was a very simple way to do it. We tried, and it works quite well. Then they are obviously now we are maybe more interested in open vocabulary. And here you can do something quite similar, which is you take your mask, you go to Kipf, and you maybe try and get a descriptor for your mask, and then you can try and fit it to your vocabulary that you will have with text. And I would like just to highlight two works that are presented at CVPR, which are doing something alongside this. The first one is zero-shot unsupervised transfer instance segmentation, where they try and propose a unified semantic and instance segmentation. And there they use a frozen text encoder that produce a set of text features. So unfortunately, here you are still limited by a finite set of text features. It's hard to have the entire world to you, but they achieve good results and are able to do open world segmentation. Another work is zero-shot referring image segmentation, where in this work, it's a bit different because the task here is you have an image, you have some text, and you want to know where in the image is the text that you're talking about. But what they propose here is to use free solo to generate the mask. And then using a global local similarity, they are able to assign particular patches to a certain text. So a particular mask to a certain text. So yeah, so that was quite interesting. So that concludes my talk. So in terms of conclusions, what we have seen is that it's possible to discover objects with no annotation. It's quite easy to extract, to use methods to extract for single object localization properties from the Dino features, for instance. That we've seen that training boosts results and increase the number of localized objects. And finally, that it's possible to assign a closed open class to mask boxes. In terms of remaining issues, obviously, how can we further improve results? We are already, if I remind you, we are in a fully unsupervised setup, so we're already achieving pretty decent results. But we are still limited by the abilities of the self-supervised features. So could we think of a way to produce representation that will be directly tackling the task of object localization? And actually, Thomas will be later talking to you exactly about this. So that's it. Questions? Yeah, sorry, I think he was first.
Thank you for the wonderful talk. I had a question about models like Dino.
Mm-hmm.
So these are using object-centric images,
yeah,
which already gives a hint,
yeah,
as into what's foreground, what's background. What do you think would be like, how would you say like these could be extended to 3D, where you have like a 3D scene like here, you have the point cloud representation of it,
mm-hmm.
and there's no hint into like what are the foreground and background?
That's a very good question, and it's a remark that comes a lot with reviewing process, that Dino is curated and therefore includes a certain level of supervision. So I'm not working on the task of self-supervised itself, self-supervised learning itself, sorry, but I know there are work that are trying currently to go beyond ImageNet and to try and explore. I think the 3D world that you described can be a good cue producing space. In particular, I don't know about indoor, but in outdoor, you can really use unsupervised methods to localize segments. So you could use that to maybe crop your image around that object, for instance, and you could use that those type of hints. I don't know about indoor. I'm not that familiar with it, but I think that's a good comment, and I hope that there will be more working on going beyond ImageNet. Yeah, for sure. Thanks. Yeah.
Thanks. My question is about your state-of-the-art method, which is called font.
Mm-hmm.
And I see that your method is based on a very important assumption,
Mm-hmm.
that the background tend to attract little or less attention of your pretext model,
Mm-hmm.
right? Like Dino.
Mm-hmm.
So are there any theoretical supports for this assumption?
No, they are not. And I think even in the why keys and not queries and not values features is like still a question ongoing. I think it's quite linked to maybe the previous question. ImageNet is object centric. You have your image, and basically through training, what I assume is happening is that the model is going to learn to ignore in the crop decision making, like trying to produce one class for the two crops. Finally, the background is not going to give a lot of information. So I assume that through training is going to learn to assign little attention to that. But that's very empirical.
Okay, I see. Okay, thank you so much.
Yeah, thank you. I have no idea of the time. Yeah, did I go fast? Okay. Yeah, go for it.
I appreciate this is unsupervised or self-supervised learning, which is, very impressive and exciting. But with models like the segment anything model out there, should I just use that and hope that it will segment the objects that I'm interested in? Can you use that as like a starting point or compare how your results do to something like that? Which should I use?
Yeah. Well, I guess segment anything is supervised, so I expect the masks to be better. I don't think we are comparing to segment anything in terms of results. I think it depends what you want to do. I do think that we can do an unsupervised segment anything. I think that it's possible.
Okay.
But in terms of performances, segment anything has a lot of well-designed tricks and annotation that have been made by humans. So I guess I will start with this.
Right. Okay. And then maybe fine tune it a little bit.
Yeah.
Something like that.
Those methods are, I think those methods are great in the helping discovering any objects. That in segment anything, there was a nice talk yesterday, and they said that the problem that they had is that during training, the annotator has to select a mask. And there was a strong bias because annotators were mainly focusing on objects that they like. So person, car, things that they will tend to look at. And so what they had to do at some point is to try and come up with a solution. So they pre-annotated all of those objects and then asked the annotator to annotate the rest. So, but I guess you always have to, with this problem, which is where does the human eye go? And can maybe those type of model be helping with actually not being biased by human supervision?
Makes sense.
Yeah.
Awesome. Thanks.
Yeah, you're welcome. Yeah.
Okay. Actually, it's related to the answer you just made to the previous question. One of the interesting usage of all these fully unsupervised and sometimes fast methods for letting objects pop up is in the context of annotation. So as a tool to to speed up the task and to help the annotator. So could you give a bit of context on the use of these methods within a data pipeline with human annotator process?
Yeah, that's a good question. I think, and that's also a place where segment anything is used in the pre-annotation. Yeah, I guess when you want to help the annotator doing a very annoying task, which is to give every patch, every pixel a label, having a predefined method that will highlight where to focus on, and then you'll ask the annotator, okay, within this mask, where are my objects? What are they? Then this will be indeed helpful. But yeah, I think those methods are just very helpful in getting out of the bias of humans and maybe trying to help in general to think of the object a bit differently out of what we most frequently come up with. Yeah, thanks. I don't know if online, oh yeah, go for it.
Hi, a quick question. Do you think that the underlying assumption about the attentions would hold, for example, in medical imaging, where your foreground is abnormalities and the background would be healthy regions in it, for CT scan, MRI scan, just X-ray, for example?
Yeah, and I believe one of the first person to cite lost was a medical paper. That was I was quite happy with that. I think it has been shown that, for instance, Dino can generalize to medical imaging, which is maybe a very different domain space, but what you need are representation of the edges, etc., that it maybe is already in Dino. So yes, for sure. And you might have, I don't know, do you have like already super defined self-supervised features that have been only trained for medical imagery? Those
you can assume that you already know the labels. I mean, you know the options. You know, for example, you have a finite vocabulary of different abnormalities, but you want to discover the grounding where it is in the image. Yes, yes.
I do think that they could work. I don't know exactly how like this, but yeah, I think that could, there has been already works that show good generalization properties.
Okay, thank you.
Yeah, no worries. Are there questions online? No?
I saw one question in chat, but I'm still waiting for clarification because I'm not sure which part of your presentation refers. So I'll wait for one more moment. I have a question in the meantime, actually. First of all, thanks for a very nice talk. I was wondering if, like, for any of the methods you presented, there has been a focus on evaluation, maybe in some other papers, the people that is follow-up work beyond localization and segmentation. Like, have people looked into whether these kinds of representations you get out of these like clusters, for example, give you certain benefits for other downstream tasks, like visual question answering or something like that?
Visual question answering. I don't know about visual question answering. They have been, TokenCut proposed an extension to videos where they also include optical flow and are evaluating so on videos, which is a bit beyond image. I guess with text, it's coming. So there are already those two papers that are presented at CVPR, and I will expect more work to align text and images. But out of my head like this, I don't know exactly. So except the two ones that I presented before, I wouldn't be able to say. Oh, I think yes, there was maybe Weidi. You will talk about it. You had a work that is using both Clip and Dino, right? Oh, Weidi is online. Sorry.
Yes. Yeah.
Yes, so I guess you might talk about it later.
Yeah.
What was your second question, Thomas?
Oh, no, that was my main question. I was just wondering because, like, in the methods we're going to present later, indeed there have been these like other downstream applications, but for these kind of token cut style approaches, I haven't really seen that. So I was wondering. Thanks. So there's one more question online. The question is by Anirudh, and it's on. What does the correlation mean with respect to the actual task at hand, such as segmentation, for example? I think it was like pretty early in your presentation. Maybe you know what it's about.
What does correlation not decorrelation, correlation, right?
What does this correlation mean with respect to the actual task at hand?
So correlation, I guess the way I see it is positive similarity. So things are correlated when they are similar, and that you can compute that with cosine similarity, for instance.
Yeah, I think that answers it. Thanks.
We have a question in the room as well. Yeah, go for it.
Hi, thank you for your talk. I just had a question. In many of the examples that you shared, it's like a holistic object that's being segmented. Can you give any insights on how you might want to segment parts of objects?
That's a good question. Actually, when I was playing with founds, I tried different ways to learn the segmentation. And at some point I tried something where you have automatic centroid. So through training, you hope to learn centroid that will represent your object. I tried something like this, and that's quite related to the first work that was showing the torso and the parts of the object in the space. What I observed is that very quickly what I had was parts, actually. And I think that's why segment anything, I think, can be done in unsupervised fashion. You will highlight, so through training, I saw that appearing before going to object, you had these parts that were very easily extractable from Dino. So I think maybe that first paper can be a good first place to start from. Yeah, but definitely, I think it's possible.
Thank you.
Thank you. Yeah.
Hello, thank you for your great talking. And I have a question that in my experience, I use a very naive method to discriminate the foreground and the background. And I find when I come to some examples that I'm sure there are only one object in the image, but sometimes it will go to the background. For example, if there a man before a tree, and the model it may focus on the tree in some occasions. So, do you make some failure examples when the model focus on the background, not the foreground you expected, and what do you think? Why this is coming and how to solve it? Yeah.
That's a good question. I think there is a strong assumption in the work that we have shown is that you expect background to be highly correlated, quite uniform representation throughout all the patches. But if you have an object that is smooth, I will expect this to be picked up, because then basically when you're considering the least attention or the most correlation, it will go to the smoothest zone in the image. So that's a good point, and I think that can be fixed through training. So I was thinking about also when your object is, most of the image is the object, and sometimes when you have no object, you still, we've found, for instance, when you have no object, you will still have a segmentation, which you don't want. And I think through training with negative examples, so showing empty images and saying there is nothing here, you can maybe tackle this.
Okay, thank you.
Thank you.
Hi, I have another question. So does this kind of models can handle a multi-object detection? Like, let's imagine if we want to do a counting people system in this room, and people sitting in the front are larger than people sitting in the down. So these kind of models can solve this task?
So you mean scale, if we have different scales? I think they have methods that are like trying to explore scale. Free mask is one of them when they have queries of different scale. And that's a good point. That's something that I think can be enforced. Maybe it's not designed, those methods are not designed for it. However, we found, for instance, we showed that we were able to localize quite small objects. Yeah, I don't have the image here, but people doing on the field, playing football with different scales, and we were still able to separate them. If you have a crowd like this, which is quite dense, I don't know how well the performances will be. I think, yeah, dense make it harder.
So in that case, do you recommend to use the systems like SAM, right?
Yeah, I think in general, we are not competing with SAM here. I guess we might be at some points, but SAM generates so many more, but maybe too much segments actually. I guess for industrial, when you are just considering all of the segments, what is the object, what is not, So maybe Sam with something with a bit of training to know what is the object, what is not, can be what you're looking for. But yes, some segments are a bit better, I think.
Thank you.
There was one last question. I don't know, do we have time? Okay, let's this be the last one.
Hi, thank you for your talk.
Yeah.
I think my question is more about how you evaluate these methods. And so I guess it's the fact that for let's say sparsely annotated data sets like Pascal and even Coco, there is a question about what objects we care about finding as opposed to what the model may find. So
yeah,
I guess the question is, have you evaluated or considered evaluating models like that in more densely annotated data sets like Elvis, for instance, to see whether mistakes that the models make, let's say mistakes, are actually mistakes, or if they simply register objects that may not be of interest in the datasets that we typically evaluate, so desks and object parts. Stuff like that.
Yeah, that's a good point. We haven't, I guess, because of time during submissions, you don't. But it's a very good point, and most of the papers, when they show limits of, and they show like, look, we have discovered something that was considered not an object in the dataset. So basically, trying to. So I think it will make a lot of sense. Actually, that's a good point. Maybe Elvis is one way we should evaluate all those methods. Yeah, good points. Thank you. Okay, so I think this is done. So we have a break, 15 minutes break right now, and we'll come back for Thomas Kipf and Weidi Xie presentation. Thank you. Thanks for staying with us. So we are going to go to the second part of the tutorial that will be held. Thomas is going to start. So Thomas Kipf is a senior researcher scientist at Google DeepMind. He obtained his PhD at the University of Amsterdam, working with Max Wehling. For his PhD thesis on deep learning with graph structure representation, he received the Ellis PhD Award 2021, so quite a big award. So we are very happy for your talk, Thomas. So go for it.
Yeah, thanks so much for the introduction. As Oriane mentioned, I'm Thomas. I'm a senior research scientist at Google DeepMind, and today I'm going to talk about self-supervised learning with object-aware priors. And this talk is a little bit different, I guess, from it marks a bit of a difference from the talks you've seen early in the tutorial, in that we're now talking about kind of end-to-end trained deep neural networks and how we can integrate particular priors into those architectures to get some of those benefits sort of for free that we've talked about earlier, which you could also approach via, say, for example, certain clustering techniques or via, for example, pseudo-labeling strategies. And so here we're really going to talk about kind of end-to-end learning and how we can enrich neural networks with particular priors. I also want to say I apologize that I couldn't make it in person. This was kind of an unexpected thing that came in between, but I'm happy I can still give the tutorial remotely, and we also have quite a few remote participants, as I can see. All right, so object-aware priors in deep learning. So the goal here is really to build neural network models that can abstract and represent objects in their architecture, so like somewhere in the model. And one question one might ask is why would this be an interesting goal? Why would we want to do that? And so if you look at the world around you and like everyday kind of scenes in your physical environment, you quickly come to realize that the world is highly structured, at least like our everyday environments, like you have. Like these images here, traffic scenes where there's rich structure in terms of like cars and individual traffic participants or animals, or even in this kind of toy object in this Newton's cradle example on the bottom right, there's very rich kind of even hierarchical structure. Like you can perceive the entire thing as kind of an object, but also you can richly reason about like, or imagine what's going to happen next based on like the physical structure of this object and its particular components. And so that raises a question, kind of why do we care about objects in say perception or in the machine learning in general? And one particular aspect is that they're really core to human perception. So if you want to learn from human intelligence and human perception anyway, then one interesting phenomenon we should be able to model is like objects and the things that they facilitate. Of course, this doesn't have to be something that has to be explicit somewhere in the model, but the model should facilitate learning those kinds of representations. And objects can also be directly useful for certain downstream tasks. Like, for example, you can have like detections that you get out of a detector model, and then you can use them in like some more classical pipelines, or use them to plan like trajectories in self-driving cars and so forth. So just objects per se as a kind of structure of a representation is a really useful kind of entity. And I don't think I have to convince you, because it's a very classical representation in computer vision tasks, and many computer vision tasks are built around localization of objects. And finally, one aspect that I think is often assumed kind of implicitly is that these kinds of object representations are really good at facilitating interpretability, as opposed to having like a big kind of deep neural net just producing some kind of like downstream output, like a language output. If you have some kind of intermediate object representations, they really help you interpret kind of what's happening and how things are grounded. And at the same time, it buys you things like compositional generalization and data efficiency. Like if you, for example, want to simulate the world going forward, if you know how kind of if you've ever seen like two particular objects collide, you can immediately generalize to kind of objects with slightly different new appearance, and can imagine kind of how the future is going to roll out in that kind of collision. And so there's kind of a rich history of studying object priors and objects in cognitive science. And this has really spawned also a branch of the literature in machine learning that cares about integrating these object priors directly into neural network models. And very often, like the kind of overall kind of framework looks a little bit like this. And I think this is a nice mental framework from this paper, the survey paper on the binding problem in neural networks from Klaus Greff and others, where basically you will have, like, on the one hand side, some kind of unstructured input. This could be an image, and you would like to segregate this kind of really unstructured high-dimensional signal into a structured representation. And like a very natural structured representation, so just say one representation vector per object. And of course, this really facilitates also like computer vision tasks like object localization. If you have a representation per object, then that representation must be bound somewhere to the image, and then you can localize it and so forth. And so this problem of like how you can perform this information segregation, representation, and composition is really the core problem we want to address when building object priors in neural network architectures. And the goal is often also then to learn about objects with minimal explicit supervision. But an interesting takeaway here is that these kinds of architectures, they don't really care if you kind of train them unsupervised or if you explicitly supervise them, if you have labels. You can basically do both. But if you don't have supervision and you have the right inductive biases, then you can also get objects for free. And that's kind of what we're here for today. And another interesting aspect is that these methods are really kind of scalable via end-to-end learning and self-supervision, which is like one of the core recipes we've seen being successful for, say, large language models and like the recent successes in generative AI. Where really end-to-end learning and self-supervision are like two core ingredients. And if you can get like the same kind of breakthrough for object localization without having to collect massive data sets, and especially if you want to go to more complex setups like videos in 3D, this might be really beneficial. Now, object representations can take various forms and shapes in neural architectures, and there are, like, over the years, there have been more or less three main categories that the community has focused on, and there exist many other kind of less explored choices, which I'm not going to go into detail about today. But the main categories really are sequential slots, Bayesian slots, and instance slots. And I'm going to explain like the details in a moment. So for sequential slots, we typically assume we have an ordered sequence of vectors. And that is basically, a typical example could be you have an image and you extract one object at a time. And that is similar to kind of like a visual saccading mechanism where you like pay attention to one object, you abstract it, and you look at the next object and so forth. And one nice property of this is that it doesn't really matter how many objects in the image you are. You can just sequentially go through all of them, and it's therefore a pretty general mechanism. Then there are spatial slots, which are also very popular in various architectures, and that they basically assume a grid of vectors. And this is basically a patch-based representation if you have an image as input. And in those spatial slots, you would take for example, the patch that captures most of the object and just say, okay, this is the patch that corresponds to the object, and everything you care about reading out for the object, you read out from that patch. And finally, there are instance slots, and those slots are effectively permutation invariant sets of vectors. And those are pretty popular these days because they reflect a property of objects in the real world. Like if you look at the world around you, objects, they don't really have, there's no particular meaning whether you assign a label 1, 2, or 3 to a particular object. So there's no particular natural ordering or global ordering you can apply to objects in the world. And so as like putting the same kind of symmetry we have in the world about objects into the representation, it's one of those lessons in terms of like building neural network architecture, is something that can buy you a lot of data efficiency. And so these methods, basically you assume a set of vectors and you somehow route the input to these individual set limits. Now, if you think about like the supervised literature on detection, you might recognize some of these earlier methods. And I'm going to explain a bit the connection in a moment. But I would like to give a selected method overview of like earlier methods that have really tried to build neural network architectures with these inductive biases for unsupervised detection, unsupervised object learning, or even generative modeling. And so for sequential slots, you have methods like attend, infer, repeat, or Monet that essentially have like an iterative attention mechanism that at every time step extracts some object from the input, represents it, and then you can train it, for example, by self-supervision to decode that final image again. You have spatial slots, and for those there are several techniques that gain popularity, and these typically involve learning a grid of image vectors, and then you, for example, learn particular presence probabilities or like a depth ordering of the objects, and a per grid thresholding that determines whether there's an object in this particular grid location or not. So there's a lot of discreteness in these kinds of methods, which also comes with some problems, but the benefit of those approaches is that they can really scale to a lot of objects very easily. And finally, you have instance slots, which I think is the category of methods in this part of the literature that has really gained most of attention recently. And one prominent example here was iodine from 2019 from Klaus Greff and others, and later on slot attention, a method we've developed for iteratively by an attention mechanism extracting objects and mapping them to a set of slots. So there are many, many more papers in this field. I'm going to cover a few more in the coming slides, but of course, this is not going to be an exhaustive review of the field. But any of the papers I'm linking here will be a good starting point if you want to learn more about this area. So just want to highlight, before we go into the actual methods, what you can actually expect to get out if you take any of those kind of latest methods that use instance slots and end-to-end kind of deep neural networks that include those kind of slot inductive biases. Then these are kind of the examples of what people have built so far. So for example, for image data sets, you can with these kinds of methods by now, and this is a very recent paper from iClear, get somewhat decent like localization of multiple objects and multiple entities in an image. You can get 3D consistent representations, even for like textured scenes or real world scenes like Street View these days. And you can also get, like, for example, in this Waymo open example here, get like segmentation and tracking of cars without any extra supervision on top. So before we go into some of those later methods, I want to start with a few examples on like these early approaches, for example, for sequential attention. And so one particular impactful example that I already mentioned earlier is Monet. And that was one of the first methods that really made this kind of sequential attention process work to extract objects without supervision. And so ultimately what it does, it has an attention network and a representation network, this component VAE. And it sequentially attends into the image and produces an attention mask that extracts a particular object or a background or a particular kind of segment from the input. Then the component VAE encodes that into one latent variable. And then together with the mask and the reconstruction of the VAE, we can get a masked reconstruction of the image. And then basically step by step, the model continues by producing a new mask that now has to explain what hasn't been explained before. And so bit by bit, you get like an explanation of the entire image, and you get like one component at a time. And one benefit of this is that this is really kind of agnostic to the sequence length. So you can, if like an image is a lot of objects, you can just run this model for many, many steps, and it'll extract a lot of objects. But one downside is, and this is really like one of the main reasons why this hasn't recently been adopted too heavily, is that it requires n calls to an autoencoder to like extract n objects. And if you have 100 objects, that's a lot of calls from an autoencoder for a single frame. And if you imagine applying this to a video, this gets very, very expensive. And so that's where kind of spatial slots come in that really break down the sequential process into kind of fully parallel grid-based mechanism, which is very efficient on modern hardware. And so here, you effectively start again in this method space here from an input image. You represent that input image, for example, passing it through a CNN encoder as a grid of feature vectors. And then you parcellate those feature vectors, for example, in the presence probability, in a kind of a depth variable, and an XY coordinate or latent variable for where the object should be in image relative to that particular patch. And then you can train a model via reconstruction by having some kind of bottleneck or prior on those latent variables. Now, this scales to many objects per scene, but it has the problem that effectively you have to put a prior on all these kind of details, and you have a binary indicator per grid location that tells you whether an object should be there or not. And as you can imagine, these things are kind of brittle to optimize. And you also have the problem that you have a certain kind of size prior. If you have objects that span the entire image, this is something that cannot be well represented with this kind of representation, at least not in a trivial way. And there are many kind of related methods like spare, scalar, and Simone. Simone is a method that uses transformers and overcome some of those issues, but it's still somewhat limited in terms of its applications. And finally, we have methods that map to instance slots. So this is kind of this representation where you start from, say, an image, and you map to a set of vectors. And of course, if you think about like the literature now in terms of supervised detection models, we had representatives of these different classes of models. Like for grid-based models, you have things like faster RCNN and these kinds of approaches, or single or multi-stage detectors, or two-stage detectors that effectively operate on a grid, and then for every grid location predict some kind of objectness. And then for instance slots, a particular representative that in a supervised literature, of course, is very impactful, was the detection transformer that precisely kind of takes this paradigm of representing a set of objects just as a set of vectors and predicting that using a permutation symmetric architecture like a transformer. And so here we go a little bit back in time to a method called iodine that was one of the methods that kind of pioneered this kind of set-based approach for object representations. And effectively what that paper did is it starts from like some initial guess, some initial initializations what these objects should be, and then iteratively refines that representation via a number of kind of decode and encode steps. So you kind of have the representation of what the object should be, you try to decode it, you look at how well it explains the image, you compute some error, and you encode it again to compute like a correction step. And over time, you end up at like a crisp decomposition of the image. Now, this is parallel and iterative, so you don't have like a linear dependency on the number of objects, which is great. But one big disadvantage here is that it still requires multiple encode and decode iterations. You still, for every iteration here, you need to decode your latent variables, one for every slot, check with the input, and encode it again. This you have to do like 5 times or so to kind of slowly converge to a solution. And again, this is very expensive, especially if you want to run this, for example, on a video. And so in 2020, we looked at this, the state of the literature at that time. And so we thought, okay, like these instance slots are really great, but to really make them usable, you need something that is much faster and doesn't kind of rely on this like iterative encoding and decoding all the time. And thanks to attention mechanism, we can effectively overcome this issue by doing attention-based iterative grouping. And that's the core idea behind slot attention, where basically you again start from an encoded image that's passed through an encoder into a grid of vectors. But then you have a cross-attention mechanism from those initial latent slots that initially just have a random guess of what the object should be, and then iteratively just cross-attend into the input to refine the representation of the object. And after just a handful of iterations, you end up at like a pretty crisp kind of grouping of what the object should be based on the input representation. And the nice thing about this is it only requires a single call to the encoder and to the decoder. So you don't have like an iterative dependency. And the attention mechanism here is very lightweight. So this is a relatively fast method. And of course, it's very similar to what has been successful around the same time in supervised detection with detection transformers. And I just would like to go a little bit more into detail and look at how the slot attention mechanism works precisely, just to give you a bit of an understanding of what like the core considerations are and how it connects to some other algorithms. And so in slot attention, you start by having like a set of input vectors, and these are usually the feature maps from your visual backbone. Like this could be a CNN, this could be a vision transformer, and you obtain also position embeddings. So up to this point, this is pretty much exactly the same as a detection transformer. And this is basically a set of vectors that describes the image grid. And now you start with, you have to start with some kind of initialization for the latent slots, because they don't come for free. They don't come from the image grid, for example. So you have to start with some way of initializing them. And one of the easiest ways is to just initialize them by drawing them from a normal distribution. So completely at random. You can do this either at every training or inference iteration, or you can do this just once at the beginning of training and then fine tune or learn the initialization of these slots. And then for a number of iterations from time steps 0 to t, so these are the time steps you see in the right-hand side of the figure, we effectively do the following. So you have your inputs, so these are the encoded input features. You have your completely random slots at this point, and you perform an attention mechanism by basically key transforming the inputs and query transforming the slots, and that's basically just a standard cross-attention mechanism. But then when we compute the softmax over these normalized scores, so the tau here is a temperature normalization, as we usually do in cross-attention, then we normalize the softmax over the slot axis. And so this is the core difference between regular cross-attention, for example, to image features in a detection transformer and any kind of typical cross-attention mechanism, which is normalized over the input axis or the key axis. Here we normalize over the slot or the query axis. And the reason we do this is because we want every slot to exclusively bind to particular areas of the input. And so the normalization here is visualized here. So it means that all the attention maps, they sum to 1 across the slots. And that means if one slot already explains an object, a different slot will be downweighted for that same object. And that's not the case in regular cross-attention. And so effectively, this feels a bit like a clustering mechanism. So kind of slots have to commit to the particular objects they capture. And now, I mean, the reason why usually in cross-attention you normalize over the inputs is because otherwise, once you compute the updates using the weighted sum, things would explode because you kind of have like an unnormalized sum. And we fix this in slot attention by renormalizing that sum. So instead of a weighted sum, which would be just multiplying the weights of the value transformed inputs in the sum, we perform a weighted mean, which means we also normalize over the sum of the weights. And with that renormalization, things get stable again. And then we can write the updates to the slots. And we do this with a learnable gated recurrent unit, but in principle, any other kind of learnable mechanism would work here. But a gated recurrent unit is nice and stable because we actually share parameters over these iterations. Again, this is a choice that's not absolutely necessary, but this is something we found nice as kind of an iterative optimization procedure. In practice, also, when you implement this model, it's recommended to use like layer norm on the inputs and the slots, but those are kind of just small details. Now, to really understand what's going on here, I think it's nice to make the connection to clustering. And because we heard a lot about clustering in Oriane's talk earlier, it's nice to kind of see how this kind of differentiable module that now defines a lot of the kind of object discovery in end-to-end deep learning architectures, how this connects to more like classical clustering algorithms. And so the core difference here is really that, again, in clustering, we start by initializing the classes in some kind of way. Here, we just call them slots and initialize them from a normal distribution. And then for a number of steps in clustering, you would compute a squared Euclidean distance usually, or some other kind of distance function to obtain the scores. And again, you would compute in soft k-means, which is differentiable, you would compute responsibilities for each cluster center to each input. And again, here, this corresponds to a softmax over the scores normalized over the slot axis. And similarly, in soft k-means, you would do a weighted mean to aggregate the inputs. And finally, you just write the updates into the slots. And so the core difference between these two algorithms is really that in slot attention, we just sprinkle parameters everywhere and make everything learnable. Whereas in clustering, you would kind of directly optimize for like minimizing the square distance between the clusters and all the inputs. And in slot attention, you minimize whatever distance function is useful for the downstream task. And so if the downstream task is reconstruction, then the kind of clustering you optimize for is like whatever makes reconstruction the easiest. Or if the downstream task is future prediction, we optimize whatever clustering makes future prediction the easiest. And so that is very beneficial because we don't have to rely on the inductive bias of the clustering algorithm alone, but we can really still flexibly learn in kind of what space we want to cluster. And this also explains why slots have to compete for explaining parts of the input in slot attention. And so now if you look at how this model can be kind of trained without supervision, which is the main reason we're here for today, of course, you can also train these models with supervision, so nothing prevents you from doing that. And in fact, methods like the segment anything model, which has gained a lot of popularity recently, has a very kind of similar structure. It uses kind of a set of latent slots, and these kind of are directly supervised with mask supervision. And so if you want to train this model now unsupervised, what you would do is you would take an image, pass it through a CNN, apply the slot attention module, and then one of the easiest unsupervised tasks you can do is just reconstructing the input again. And now one question is like, how do we go from slots again to inputs? And one solution for that is to apply a CNN decoder independently per slot and let the CNN decoder produce also an alpha mask. And then we can use those alpha masks to recombine the images into a single image and apply a reconstruction loss. So basically every slot decoder here reconstructs an RGB alpha image, and together they make up a single image that we apply the loss on. And so what like this very simple method, just by training it with autoencoding can do on these kind of relatively simplistic clever data sets, is that first of all, it can obviously reconstruct the input, but that's not a big feat because it's like there's no denoising happening or anything. It's just like a deterministic autoencoder. But on top of that, it learns to kind of cluster the scene in a very meaningful way. Like it learns to keep slots empty if they're not needed. And it clusters the scene in terms of like the meaningful object components, and even captures like occlusion properly. And like even if you now would delete number slot from slot 11 from the representation here, what you would see is that slot 5 is fully revealed, and it would complete the sphere and render the entire sphere. And that's something we know as amodal completion in human perception, and that's something that these models kind of naturally do as well, which is quite exciting. So now one question is like, how can we apply that method to videos? And there is a very simple solution that exists when using instance slots in particular. We can simply use the past slots to be discovered in the past time step as initialization for the clustering in the next time step. And that's special about these instance slots, which it's a benefit you don't get from grid-based representations or from sequence-based representations. And the same holds for supervised methods. You cannot easily kind of extend that to tracking in video, whereas here there exists a very simple solution. And what that looks like in a picture is something we've done in SAVI, slot attention for video, but it's also been done in very related methods, RNNEM and OP3, for example. And you simply have like a time self-connection over time in the slots, but everything else is per frame independently, like the per frame encoder, per frame decoder. But there's just a small connection over time, which is again a very kind of, because that latent representation is very small, this is very cheap to do. And as an effect, you get like tracking of objects for free, like in these robotic examples here. Now, the same trick applies for 3D. And again, here instance slots are very beneficial because they're decoupled from the grid. They decoupled from the input grid. And that means no matter from which perspective you observe a scene, those slots will stay in place. And so you can ground them in various different observations of the scene. And this is, for example, done in this paper, Unsupervised Discovery of Object Gradients Fields, or UORF, from ICLE last year, where instance slots are basically combined with a novel view synthesis objective. And they're basically trained in a way that you start from an input image, you encode it, you apply some version of slot attention to obtain your object latents, in this case, also background latent. And then you have a per token or per slot nerve that renders the novel views. You apply an L2 loss in pixel space and train the whole model end to end. And what you get out of it is like per slot kind of binding of objects, and you can then manipulate those scenes, you can render novel views, and these objects are really decoupled from the pixel grid, which is nice. And there's some more recent work which scales this to more complex data set, for example, like OSRT. So far we've covered relatively kind of simplistic scenes, like basically simple like synthetic scenes, like clever and simple kind of 3D scenes that might have some texture, but overall are relatively simplistic in their appearance. And of course, what we're here for is like, how do these methods actually perform in the real world? And like, how can we make them work and do something reasonable when applied to real data? And the answer is basically, if you apply this to data like these images from MS Coco here, is that if you just take these naive recipes I've shown earlier with just auto-encoding with like very simple architectures, you get something like this. And this is, of course, a big disappointment if you're following this literature. And this is the reality is that this has been like the status of the field for of these end-to-end models with object priors for about 5 years until more recently, multiple independent papers have been able to overcome these issues. And so what you get here very often is the model just collapses into some uninteresting failure mode. So these slots, they just bind to some grid location. They effectively just cluster the positional code and fully ignore the visual input. And they still represent whatever happens within each patch or within each of the kind of segments, but they effectively discover a patch-based representation as a representation they would like to learn for reconstruction. And the problem is that on these kind of highly textured and diverse images, slot attention, also many, most earlier related methods, they typically collapse if you just apply them and run a kind of pixel-based reconstruction. And so now the question is like, how can we overcome it, and what is actually the underlying problem? And so what people have found over the years is that models are typically just like those that were published in initial papers, because they were trained on these kind of simple toy data sets. They were just too small and not expressive enough. So often just a few layers of a CNN. And of course, as we know, like those will not do very well on more complex structured data. And so only by just using better backbones and using things like data augmentation, these methods can already do a lot better and get quite a bit further. Another problem is that objectness can be ambiguous. Like we talked a bit earlier about, Patrick especially talked about what is an object, and there are so many definitions and so many different use cases. Often we just care about like the salient big physical things in an image, but often like objects can also be like more like abstract concepts, or just generally like a thing that can be bound to like some kind of, or grouped together to some kind of high level representation. And so that also comes with the question of like abstraction level. And because of all this ambiguity, like this task is often not very well defined and needs potentially some additional kind of side information to really be resolved. And optimization of these models often can also be quite brittle. And so you get things like collapse of these models. So in terms of solutions, we're going to hear in Weidi's talk in just a few minutes that training with multimodal signals can actually help a lot. If you don't just look at images purely, but if you look at some other data that you have, you can overcome a lot of these issues. But it can also disambiguate, especially if like the problem is really ambiguity of objectness. You can disambiguate things like with partial or weak supervision. Like you don't have to do everything unsupervised, because often we just have labels for certain things, and you can kickstart a model like that. And things also like, as I mentioned before, architectural improvements, pre-training and data augmentation, these are obvious things, and they definitely work, and they definitely help. And so I'd like to focus on one particular paper that was presented at iClear just a few months ago, called Dinosaur. And as we've already heard in the past presentation, like Dino features are great for kickstarting kind of object discovery. And the same applies if you like look at these end-to-end models, like doing something like slot attention with object priors. And you can basically start from pre-trained Dino features, apply slot attention on those, and instead of reconstructing the pixel, you reconstruct the Dino features. And that can already overcome a lot of these issues. Like here, slot attention has quite a bit of issues, and Slate is a method that maybe has a little bit of object specificity, but still has a lot of issues. And that is basically a slightly scaled up version of slot attention with a stronger decoder and some auto-encoding pre-training. But Dinosaur really like represents a big jump just by using good pre-trained features. And on top of that, Dino explores two different decoder designs. And instead of using a CNN decoder, they like play around with like a per pixel or per patch decoder that decodes every slot into each patch individually. And then again, together with an alpha channel, performs a weighted sum and reconstructs the entire image that way. Or a transformer decoder that auto-regressively decodes the patches of the Dino features. And so both of these perform really well. And ultimately, if you remember those results from like the last presentation, like Token Cut, which was doing quite well under this Qualog metric on Coco, with Dinosaur, you can still get quite a bit of a big jump. And that was kind of the first time that these kind of end-to-end object-centric methods really made somewhat of a dent in this part of the literature, which was previously mostly dominated by pseudo-labeling strategies and kind of multi-stage approaches. There's also more work now. There's quite an explosion also in submissions at iClear this year. And there's one paper I think that stood out to me in particular that I have to say this is a paper that is still under review. It's something I found in the archive. But effectively what they do is they apply solid attention on, again, VQVAE or dino features. And now they use a diffusion model as a decoder. And that can really overcome some of the also like generation problems the earlier models had. Often they produce blurry generations if you use them also as a generative model. But now if you use a diffusion model as a decoder, you can really get really crisp generations of the scenes while getting the nice object decomposition. So you not only have like a segmentation model now, but also like a compositional generative model as a side effect. And you can train the same thing now on MS Coke when it gets somewhat decent result for a model of this class. Of course, this is still quite a big gap to supervised approaches, but there's been a lot of progress now and all of a sudden in the last year. Now we've mostly focused on generation type approaches or reconstruction based approaches. This is not like the entire story. There are also methods that are reconstruction free, that are trained also kind of end to end, that don't even start with a pre-trained kind of dino backbone, and that also perform quite well on these kinds of problems. And one example here is Odin, or object discovery and representation networks. And effectively what they learn is they learn an object discovery network that takes a common backbone applied to an image, and then just applies k-means clustering, like really discrete hard k-means clustering on these tokens to get clusters out of them. And then they perform like a contrastive loss that they call the Odin loss that is very similar to BYOL in terms of the objective and the training mechanism. And they learn per object representations in this step. And so basically it's like a method that iterates between discovery and representation, and over time both of these improve. And so without doing any reconstruction in pixel space or latent hash space, you get somewhat decent localization. Of course, there's a big gap to supervised models that's still to be solved. Now, because we've mostly talked about segmentation so far, I just want to briefly highlight that these end-to-end models, they also enable other things beyond segmentations. And so these discovered object slots, because the discovery doesn't necessarily have to be done with just decoding, you can also co-train that with some downstream objectives. They can really enable data efficient learning for certain tasks, like for example, for simulation, as you can see here in this physical, still again, a bit of a toy example, from the slot former paper, where you get really a lot of data efficiency benefits. And similarly, in a recent paper called PalmE, that looked at large-scale vision language models for robotic control and planning, and they also explored pre-training the visual representation with an object-centric slot-based model, and using that as a representation for the vision language model, which gave them a lot of data efficiency on these kinds of tabletop robotics tasks. And also for things like visual reasoning, like in this Aloe paper from Ding and others at NeurIPS already some time ago. So there are still quite a few open challenges. And although like the field has made, I think, a big jump in the last 1.5 years or so, and these open challenges are still, I think there's many of these aspects that can be overcome and that will probably receive a lot of attention in the coming months and years. But I just want to highlight a few here that stand out in particular, especially one question that often comes up in these kind of unsupervised methods is how can you bias methods towards semantic versus instance decomposition? Because it's not a priori clear what we care about. If you cluster visual representations, one way of clustering it could be according to the high level concepts, like one cluster for all people, one cluster for the snow, one cluster for the trees. Or you could have one cluster for each individual person, or roughly the spatial regions where the persons are in. And depending on architectural choices, you end up with different regimes in these kinds of models. And learning to steer that towards what we care about, maybe even just with a bit of supervision, is also an open question. Of course, bridging the gap to supervised methods, things like high fidelity generation and controllable generation for scene editing. That's something that slowly starts to become like feasible, I think, with these methods, that you basically get controllable generation via a different mechanism than language, which is what we currently use for those methods, you can then also kind of identify particular object slots and manipulate these directly. Like you could remove it, that's the simplest one, but you could also manipulate the content of it. Like you could maybe control the location or 3D rotation of an object if you really try to scale these methods. And also things like controllable abstraction via textual semantics, like you might want to via text control the level of abstraction if you care about the door of a car or the entire car or the window and so forth. And so some other open questions are really kind of how much do we want to rely on inductive bias versus labeling at scale? And I think that is especially relevant now because we've seen labeling at scale actually works remarkably well. Of course, the problem is far from solved, but there's been remarkable progress just by scaling up labeling efforts with various smart strategies, like in the segment anything model. And also questions like, do we need interaction data, like robotics data, to truly solve learning? Like, does a model have to actually interact with the environment? Or can we just learn from images, video, and text alone? And that's important because from cognitive science, like things really point in a direction that interaction is really, really important to learn about the structure of the world. And with that, I'd like to conclude. So we've talked about object slots in terms of instance, sequence, and grid-based slots. Various different architectural inductive biases and how they enable kind of a scalable alternative to supervised object learning while being compatible with the way we do supervised learning these days. And also benefits, like I think one exciting aspect is that these kinds of approaches really benefit from advances not only in representation learning, but also in generative modeling, because they can integrate with those kinds of methods. But yeah, real world results are still in infancy, and I'm really excited to see what the community will come up with in the coming months and years. With that, I'd like to acknowledge my collaborators, and I think we have some time for questions. Thank you.
Thanks a lot, Thomas. So questions, I think we have time, and there is already a question online, but so maybe we can start by that one. The first question is, can clustering path itself of the slots be related to a diffusion process? Can one learn semantic features by learning to move along such cluster paths?
That is a really interesting question. Thanks, Vadim, for asking that. So in fact, it is an iterative refinement process, and a diffusion is also an iterative refinement process. And so basically, I think we can learn a lot from these advances and maybe even solve problems like object ambiguity and kind of multiple possible interpretations from like thinking about this as kind of an iterative optimization or diffusion process. This has not really been explored, but I think this is a really valuable thing to look into. Yeah.
We have two questions maybe in the room that we can take. Yeah, go for it.
Hi, Thomas. Thank you so much for the very inspiring talk. I especially appreciate the honesty around, some of the failure modes of object-centric models, which I have, personally seen when I apply this type of models to real-world data. So my question is, so my impression is that the way we get those nice object decompositions are based on often limiting the model capacities. For instance, in the original slot attention model, we like the paper only applied, kind of one round of cross attention, of course, with iterative GRU updates, without any, self-attention or even more rounds of cross attention. And when I played around with the model, when I added, more layers of, for instance, self-attention, like they do in detection transformer, the model kind of starts to break down. And also, it seems that model capacity allocation really matters a lot, because the model is based on the assumption that every slot cannot just model the whole thing. So if you make every slot's model capacity too powerful, then decomposition kind of starts breaking down. So my question is, for supervised model, right? For instance, if you have like anything like DETR or like the latest greatest DETR, they are trying to allocate as much model capacity as possible, stack as many attention layers as possible. But if unsupervised learning is based on limiting model capacity, does that mean that we are never going to match fully supervised fully supervised learning performance?
This is a really great question, and I think it really goes down to the like some of the core problems of like some of the early methods. So maybe just one clarification: slot attention, we actually do multiple cross attention iterations in the input, even in the original paper. But I agree with like the issue around capacity. One thing we found recently, however, if you have good self-supervised objectives and high data set complexity, you benefit a lot from scaling the capacity of the model. And these failure modes tend to go away. Like in OSRT, we recently applied that to Street View in a paper that's now in the archive. And basically just take as big as slots as possible. Like we make them like, I don't know, 4K dimensional or 2K dimensional, if I remember correctly. And like those failure modes don't happen with scaling these models. So I think it really depends on whether there are easy failure modes based on the dataset complexity and also the like the kind of downstream task you use. If you just use autoencoding, there's tons of failure modes. But if you use like some kind of interesting pretext task, like view synthesis or denoising or something like that, a lot of these issues go away. And so I think in the community we can still, I think there's hope that we can scale these methods and are not limited by compression as a kind of way to drive decomposition.
Thank you.
So there are 3 more questions in the room, so maybe we can make them quick, like to the point, so we can go to Weidi talk afterwards.
Sure. Thanks for the great talk. I know you touched on this briefly at the end, but I was wondering if you could just expand. So now we've got these recent, very large supervised models like Segment Anything, where really there's a diverse range of supervision for different types of objectness, different types of object prompt. To what extent, what are the failure modes of such models where these kind of techniques still can solve and fill in the gaps? So now that we've got open source models like Segment Anything, which you can apply for a downstream task, when do you still need these kind of inductive biases and self-supervised objectives?
That's a great question. So in terms of inductive biases, I would say the gap is very, very small between something like Segment Anything and the kinds of architectures we're looking here. So ultimately, you could also swap in something like slot attention, maybe multiple heads into Segment Anything, and you probably wouldn't lose much. That being said, the question is really, when do we want self-supervision? When are we fine with whatever the annotators decided is useful for objectness at this scale? And I don't know if you played around with Segment Anything, but there are many, many cases where it doesn't give you like the object you kind of really care about and want. And so kind of linking it to language is an important open aspect. And for that, collecting data will even be more difficult, I think. And if you can find a way of doing the self-supervised, that would be clearly the most scalable alternative. Of course, it remains to be seen whether like which of these 2 approaches, or maybe a combination of both, will ultimately play out.
Thanks.
Thanks. So we have 2 more, and sorry for the online question. I invite you, Thomas, to answer afterwards. Maybe.
Online.
Hello, and thanks for the great talk. So my question relates to disentanglement of these slot latents. So essentially what I'm working on is editing 3D scenes with slot latents. And what I found is that mostly that these slot latents are specific to a scene. So they essentially encode the position, also the lighting and everything. So we right now cannot use them as 3D assets and just replace one slot latent from one scene into another scene. So what would be your ideas going forward to like make this possible?
That is a really great question. I think the answer is really scale. I think if you have diverse enough scenes and examples, I think you will, like the model will learn some abstract representations and might generalize beyond scenes. With respect to position, I mean, that will be relatively scene specific, but you might be able to learn controllable position by learning a supervised readout to a particular position and then get control via that, or even kind of find the positions in latent space that define position and control it by that. But lighting is an interesting question. I'm not sure how that can be solved without using additional assumptions.
Thank you.
Thanks for the question.
Hi, thanks, Thomas, for a great talk. You mentioned amodal completion briefly during your talk. So I wanted to ask like how that relates to understanding object similarity. Basically, because if you want to do object completion, you have to have some understanding of what the object looks like in completion and match different instances of the same object. So how would that fit in this kind of an unsupervised setting?
That's a great question. And I think just by allowing a model like this to see like a huge diversity of objects, it will, if it sees a part of object, make an educated guess of like what it could be completed with. And that doesn't, that relates to object similarity, but it really relates to kind of learning an abstract representation of objects that encodes all possible appearances. And you never need to explicitly materialize kind of a similarity between objects or something like that, if that makes sense. Thanks for the question.
Thanks a lot, Thomas.
Yeah, thanks everyone.
Okay, so for the question remaining, Thomas will reply to you, and now we will move on to Weidi's presentation. Weidi Xie is an associate professor at Shanghai Jiao Tong University and a PI at Shanghai AI Laboratory. He remains a visitor researcher with Visual Geometry Group VGG at Oxford, where he did his DPhil. I was wondering if that was a PhD. DPhil. Okay.
Yes.
Okay. and worked as a senior researcher fellow afterwards at VGG. He's been supervised during his PhD by Professor Andrew Zisselman and Professor Alison Noble. So Weidi, you can put your slide in full screen and the floor is yours. Thank you.
Okay. Thank you for the introduction. So first, the time, I'm in a time zone which is quite late, so maybe I'll make some mistake during the talk. I'll try to minimize the mistakes. Okay. So I'm going to talk about the self-supervised object discovery by using multi-modal signals. And so first, this is quite a huge topic with a vast history. So I'll try to cover as many works as I can, but it doesn't mean I can cover all of them. So if you think some of your work I missed, just email me. I'll add them into the slides. And to start with, I'm going to talk about a little bit about perception grouping, because in the literature of computer vision, usually segmentation is very related to perceptual grouping. And actually, in 1923, there's something called Gestalt principle that was in psychology, and the scientists specifically want to understand how we human perceive the incoming signals into groups. And you can see I put some examples here, and actually we group them differently, and actually the grouping should be based on different metric. So that's why I say discovering objects usually becomes a question of defining certain similarity metric and in some appropriate space. And I think that just correlates with multi-signals, because each of the type of the signal, they do have some unique property. And I'm going to talk about that in the following. So the world we live is naturally multimodal. I think I don't need to mention too much about that. This is a typical video. We have the RGB frames, and RGB frames are temporally coherent. And we have optical flow because things are moving. And you can see the background are relatively uniform. That's really because the cameraman is shooting the scene and it's static. So the objects are moving independent with the background. So that's why the foreground you can see is jumped out, but the background is uniform. And that's very good prior for segmentation. I'll talk about that later. And then the third thing is we know we have sound, because when objects moves, typically they will make sound, right? And the last one is, in the recent literature, it becomes very popular because ChatGPT, these kind of visual language model like Kipf, they become successful. So we know for videos, normally, well, not normally, but sometimes we do have narrations, right? And I'm going to talk about how to use these signals to discover the objects. Okay, so the agenda, the first thing is, talk a little bit about what self-supervised learning is and why this is important. Then talk about discover objects by using motion, by using language, and by using audios. Okay. So the first thing is, what is self-supervised learning? So we all know the successful story about ImageNet, and you just train the model. So now it seems like, to some extent, any vision task can be solved by collect a large data set, and you just define a network architecture, then you just label them, label the data, and train your model. Then good and sufficient data is all you need. That seems the successful story. And self-supervised learning is actually an alternative for learning representation. And it has a lot of good things, because the first thing is it saves cost and it's more scalable, because we know these vision language models recently, they have to be pre-trained or with self-supervised learning, because you need a huge amount of data. You can't label them all, right? And the second good thing is, we do learn from data itself. We definitely need some supervision from our parents, but not that much. Mostly we learn from self-supervised learning, right? So mainly we learn from observation, manipulation, and we learn from multi-modal signals. And that's why self-supervised learning is important. Okay? And what is self-supervised learning? I think this becomes very standard in this age, because back to 2 years or 3 years ago, I have to explain to everybody what is self-supervised learning. But now I think people know better. It's really just a form of unsupervised learning, and the data itself can provide the supervision. And the idea is, like on the right, bottom right figure, that from Yan and Kong, the idea is really just, you have a full signal, you hold some of the part of the signal, and you use the rest part to predict whatever you hold it. It's really like BERT or MAE, these kind of things are typical self-supervised learning, okay? And in self-supervised learning, the task we are optimizing usually is called proxy task. So when you solve the proxy task, the network is forced to learn something we really care. And in the next few slides, I'm going to talk about one of the proxy tasks, which is reconstruction. We solve that task, the model actually learns to discover the objects, okay? And the part one, discovering objects by exploring motions. So why use motions? Because motion is very powerful cue for discovering the objects. And in the literature, actually, some of the scientists really define the objects by motion. Like Gibson, he really defines, what is an object? Its detectability is the possibility of moving a body independently. That's called objects, right? And for these tasks, what we really care is just, these are the videos, and you really just want to segment the salient objects from the video, because salient objects, mostly in the video, is just something moves. If nothing moves, you don't pay much attention to anywhere in the video, but anything moves, you immediately pick it out. I'll give you an example here. So this is a camouflage video. If things doesn't move, it's very hard to focus on anything. But if, the insect moves, immediately you focus on it, okay? So that's why motion is a powerful cue for discovering objects. And to use the motion to discover the objects, there are actually many different methods, and I classify them into two branches. The first one is reconstruction-based, and in the reconstruction-based, you can reconstruction the flow or the depths or even the RGB. And the other one is sim to real, meaning you can train on simulation data, and the model can transfer to the real videos. So these are the typical methods. I'm going to pick some of them and give a bit details. Okay. So the first one is reconstructing the flows. And the first approach I want to talk about is this called contextual information separation, because it's very unique from my perspective, because when I started this field, I feel this method is so interesting. And the idea is you train an adversarial contextual model. So it's trying to reconstruct the flow, but it's not to say you have to reconstruct the flow as good as possible. It's the opposite, meaning you have to reconstruct the flow as worse as possible. So the fundamental assumption is, in the optical flow space, the foreground and the background are independent. That means, so if you have a network, say on the left, you have a segmenter. If the segmenter takes the RGB image and the flow as input, it will give you a binary mask. So if this binary mask is perfectly segment the objects, then for the second impinter, it can't impint the flow back, because the background and the foreground, they are mutually independent. If you mask one out perfectly, the other can't give you any information to impint it back, and vice versa. So that's the idea. So that's why I say it's trying to solve a minimax problem. And yeah, so you just optimize this loss until the segmenter get the perfect dog, and your inpainter can never inpaint it back. So that's the idea. That's the first approach. And the second approach is also based on flow reconstruction. That's Thomas has just mentioned. It's really just slot attention used in the optical flow space. Because in the RGB space, the natural videos tend to be very complicated. If you just use the slot attention, mostly you can't reconstruct very well. But in the flow space, everything becomes very uniform. So you can reconstruct them pretty well. And while you reconstruct them, the alpha channel, which is, you do linear composition between the reconstruction layers, that becomes the mask, the foreground mask. And this is a little bit detailed, but Thomas has explained, so it becomes easier for me. You just pass the optical flow into an encoder, and you do iterative binding, which is actually the slot attention. So you have two learnable queries. Well, slot attention used Gaussian initialized, but here it's learnable queries, and you just do slot attention, and then you decode to reconstruct the flow. And actually, if you can reconstruct the flow, because the foreground and the background, they are independently moving. So actually for the network, they are trying to learn a trivial solution, because to reconstruct the flow in the easy way, the model tends to learn one slot represent the foreground and one slot represent the background, because as I said, they are independent. And this is the second idea, how to use flow reconstruction to learn to discover the objects. And the third idea is, it's Europe's paper 2021. So the idea is to reconstruct the RGB, but actually to me, it's still about reconstructing the flow. And that's why I say this is because they are training two branch. So here, two frames, I and J as input to the motion pathway. So the motion pathway output a flow. And what they do is they sort of like quantize the flow, because they use the mean of a region, the flow, to represent the whole shape. And they use that to warp the RGB frame and to reconstruct the RGB frame. So you can see, ideally, their flow used to warp the RGB frames becomes very uniform again, right? And actually, these the appearance pathway, they learn the segmentation model, that becomes, just cover the foreground, because that's an easy way for the model to, because every pixel on the foreground, they move the same direction and same speed. So you just use one displacement vector can represent the whole objects moving. That's the idea, right? And so these three methods are just reconstruction based. So next thing is, how can you train with synthetic data? And one of the typical example is this All Clear. It's published in Europe last year. So the core idea is, if you can't simulate video in the RGB sequence, you can simulate it in the flow space, because flow is very simple to simulate. It's uniform, right? And the idea is you simulate the video in this way. You just put the objects onto the background. So you can see it's not realistic at all. But if you compute the flow with some off-the-shelf flow estimator, let's say you use a raft, this looks fairly realistic. You just train on these flow input, the model just generalized to real videos. Okay. So because you simulate the whole video, so you have all the information, you have the model mask and you have the A model mask. A model mask meaning, the objects before occlusion, right? And you can simulate as many as possible, and you just train the model with this. So this architecture is not very, it's pretty standard. It's like mask former. So you have optical flows passed to the CNN encoder, and you have some transformer encoder to do temporal aggregation. Then you have K learnable query, so it's still object-centric representation, but it's really like mask former. And then you just decode the mask for each object, and also you decode a layer ordering, because you have the A model information. So you really can train this whole architecture with A model. The reason we have to train this with A model is really because using motion to discover objects has one bad or one disadvantage, because if things stop moving, you miss it. And you have to train the model such that the model can remember the objects. This is called object permanence, by the way. So that's why we train the model, even the model is occluded. Okay. And so for these methods I just talked about, there are benchmarks people measure the progress. And the benchmarks are SecTrack, FBMS, Davis 2016, and MoCA. And also nowadays, people also use Davis 2017, because these 4 data sets I put it here, they are mostly just single objects. And now people use multi-objects, which is Davis 2017, and also YouTube VOS, but I haven't put it here. Yeah, sorry. And metric-wise, people use mean IOU and also use some detection rate, because for MoCA, it's very hard to annotate their very accurate mask. I'll show you why. Okay. Yeah. Okay, so this is the MoCA data set. And let me click this. So this is the MoCA data set. And this is specifically collected with camouflage animals. And that's why, you know, only in the motion space, it's very easy to discover the objects. Well, it's not easy, it becomes possible, but in the RGB space, it becomes very hard. So that's this data set to test how well the motion segmentation has been progressing. Okay. And this is some of the result. I didn't put all of the result because it's going to be too long. I put some just to show you the progress on this community. And as you can see, this is the results on Davis 2016. So you can see on the real data supervised learning method, they achieve like 85.6 each. And actually, without using any manual annotation, the method now getting over 80. So it's very close to the real data segmentation, to the real data supervision ones. Okay. And this is on Davis 2017. So 2017 has multiple objects. And again, the unsupervised, just, you know, without using any manual annotation, the performance is over 64, which is pretty remarkable, I would say. And the performances keep going nowadays. But still, we have to admit that it's still a little bit behind the supervised models. And these are the results. So this is the Davis 16, so it's single objects. So you can see this is the MoCA data set. You can see in the RGB space, it's very hard to segment objects. But if you look at the flow space, you know, it becomes easier. And this is multiple objects. So this is Davis 17. For the peak one, you can see even there's severe occlusion, the model can still segment them or track them. Note that all the models have been trained, you know, completely without any human supervision or human annotations. And this is more result on camouflaged. So even the objects in the RGB space becomes very hard to see. The model still works in the flow space. Okay. Cool. That's the ideas I want to discuss for flow-based motion object discovery. And these are the references. So if you are interested in this community, make sure you check these papers. And the second thing I want to talk about is how to use language to do the object discovery. And the idea is, well, the objective is, so given an image, the task is you want to segment the objects and also classify its category. Let's say the first one on the left, you want to know this is a train and which pixel belongs to a train, which pixel belongs to the railway and the trees or the forest, right? And we want to train models on a large number of paired image caption samples. We don't want to use any manual annotations. Okay, that's the idea, or that's the objective. And typically there are two lines of research in the literature. So the first line is, can we better exploit the vision language correspondence in pre-trained clip? And there are several methods like mask clip, record, OV-SAG, and etc. Because in the 2021, 2022, there are many methods trying this direction. And the second way or the second research direction is, can we train a model end-to-end just using image text pairs via grouping and contrast learning? Because as the previous presenter has already mentioned, transformer has very good property on grouping things. So if that's the case, can we just use transformer to train the model with image text pairs? And there are several methods. Last year, the first method called group fit is also published CVPR. And this year, it's OV segmenter also doing similar thing, but much more efficient. So just to make sure we are on the same page, this is the CLIP model. They are trained with vision language doing contrast learning. And the good thing is during inference or during training, actually the classifier can be generated from the text embedding. So you can imagine the structure in the language has been inherited in the text encoder. So the text encoder has already encoded a lot of fine-grained and shared attributes between different semantic classes. So that's why it can do zero-shot generalization later. And I think this gives a scalable way to train the foundation models to the community. Okay. And the first paper I'm going to talk is how to use this clip to do object discovery. So it's called mask clip. And the idea is very simple, actually. So the idea is you have a clip. The clip can do image-wise classification, right? Just we convert it to do pixel-wise classification. So that's the idea. And you can see as the input of the image, and also you input the category name to the clip text encoder, and you get the classifier for different categories. So you just do pixel-wise classification. But of course, you have to make some changes to the image encoder, because previously, if you don't do that, you're going to map the whole image into a single vector. But now you do some changes, like you remove some of the global attention or something like that, and it becomes a relatively dense feature map. Although the resolution is smaller, but still it's relatively dense, right? And you just use text embedding dot product with this dense feature map. You get a dense, label map, I would say. And you can use this label map as pseudo labels distilled to another model. So they train a separate segmenter termed mask clip plus with a pseudo mask, and the model just becomes pretty powerful. So as you can see, the model can segment different person, Batman and Joker, and Bill Gates, Steve Jobs. So it can distinguish instances now. So this is about inheriting what the clip has. Okay. And the second one, also doing trying the same idea, but trying to use whatever in the clip. But what they do is they try to do retrieval first. So something like this. So if you want to segment one object, you go to the corpus, maybe this is image or something. You do a retrieval. So you retrieve a lot of images with the same objects. Then you do co-segmentation. Once you do co-segmentation, you know these images all contain these objects. So you can distill another segmenter. And well, similar as the previous work, you just use the co-segmented mask as pseudo mask, and you train another model by distillation. And again, the model just works to many different categories. Okay. And so the previous two works were using the clip. So now we move to the next branch. Can we train the model end-to-end? And this is the first paper, I think, called group fit. To my knowledge, this is the first paper doing this. And what they do is, again, as previous presenter has mentioned, they just exploit what the good property about transformer. So the transformer can group things together. So what they do is they do the visual entity groups just emerge without any mask annotation in the transformer. And they assign a label to each segment according to the similarity to the text embedding. And here is the detailed procedure. So one image to the model, you just break it down to patches, right? And you do linear projection. So here you have some learnable group tokens, and you pass to the transformer. And the grouping block is really just cross attention. So each pixel will be assigned to one of the learnable tokens. And then at this stage, because it's very early, so you can see the group tokens, they are very separated. They claim different regions, small regions. But what they do is they can group the tokens. Then hierarchically, after grouping the tokens claim larger and larger regions. Okay? And for training, you just have because you use image and text pairs, so you have the caption. So you just do contrast learning. You just train in this way. And this is the really detailed contrast training. So you have the positive, which is the paired image and the caption. And you randomly sample some other captions. Okay. Oh, this is random sample. They don't show it, but they show the other two. It's also positive because they can extract the entity from the paired caption and do a template, do a prompt template. They are also positive. So you can see it becomes 3 diagonal matrices. And they just train with a sum of the contrast loss. And after training, they show that in the transformer, the group token, they discover something with similar semantics. So you can see this one discovered the eyes. This one discovered the legs. This one discovers the grass or something green, I would say. Yeah. And this one discovered, I think, the face. So you can see here. Oh, body, sorry. Anyway, so the group tokens, they discover certain shared semantics. And also face, yeah. And at inference time, what you're going to do is you're going to pass the image to the transformer or the group weight. So you get, and also the dataset classes to the text encoder. And then you do the dot product, because for the group weight, you really output several tokens. So each token will claim a region, as I just explained. And they will dot product with the text encoder. You actually classify each of the groups. And that's the idea. And it works pretty well, I would say. But one of the disadvantages, I'll show you in the table later. It's very inefficient. It needs a lot of data to train the model. And so this year CVPR, we propose to improve this training a little bit by doing 2 regularization. So the first one is mask token completion. What we do is it's similar to the group bit, but the learnable token, we just feed in another model, another language model. So just to fill in the mask. So we first filter the entity in the caption, say what are the nouns in the caption, and we mask them out and ask the model to fill in them. So you can imagine this task will force the model to learn better alignment between the visual and the text. Okay. And also we do cross-image mask consistency. That means use the caption. We can easily just source images with the same with a shared semantic entity. Say for the first image you have cat. You can search another image with cat. Just use the caption because that's easy. And then use these. Both images contain the cat. So you have the group token. You found the group token to discover the cat. So you can do a image exchange. So they should be consistent. So that's the idea. And to benchmark the progress, people use Pascal VOC, Pascal context, and Cocoa objects, and evaluate on MIOU on all the classes. So this is the table, and you can see this is the group VIT results. So they train on CC 12 million. That's quite a lot of images. And we can train on CC 4 million, but still much better performance than them. This gray one highlighted is from Apple, and they train on 34 million. That's quite a lot of images. I think it's a clear submission. I'm not sure if it's accepted or not, but that's a lot of images, I would say. And they do show some good results, honestly. Okay, so these are the references for visual language, using visual language information to discover the objects. So the last thing is, we can also discover the objects by using some audiovisual correspondence. And this has been researched quite a long time, I'd say. And there are several groups in the community, like MIT or Berkeley. A lot of researchers are doing this sort of using audio to discover the objects. So due to the time, I'm going to just mention 2 or 3. So the idea is, or the objective is, given the video on the left and also the audio, its corresponding audio, can you discover the objects? So I'm going to play this one.
Sorry, Weidi, I don't know online, but here we don't hear the sound.
Okay, so it's nothing. It's similar. Well, it's nothing special. It's just the vacuum cleaner sound. And the model just tried to discover the objects. Okay, and the core idea is people do is you just train with contrast learning. It's really like how you train clip. And like I explained earlier, when you train clip with vision and language to global contrast learning, the model just learns to do the dense segmentation. And for this one, it's similar. You just do image and audio, you do contrast learning, do global wise. And actually this paper does a little bit more. And what they do is they do a softer thresholding and found the foreground objects. So those are the positive. And you found the background, those are the negative. In the middle, you define a tri map because those are uncertain region. You don't put any penalty on them. So you ask the model to tune a little bit, say, find the best boundary. That's the idea, okay? But essentially, it's still contrast learning. And with this, what you can do is, so this is just with this idea, I think this paper is 2021. Yeah, it's very old. And with this, you can discover the objects. So now I'll show you how, after you discover this object, what can you do with that? And this is the paper from last year's CVPR, is something like this. So the first step is, as I explained earlier, so you can discover the object using the audio. And what you can do is you can find these boxes, crop them out, and you do self-labeling. Self-labeling is really just clustering. So you can clustering these boxes into different categories. And with this pseudo label, you can train a detector. And that's where it can be used in real videos or real images. Okay. And actually it works. And the good thing is it works for more general categories. It's not only working for the instrument, because people may just may assume because you train on these objects, because if the object doesn't make any sound, you can't discover it at the first place. But actually, the object proposal is class agnostic. It can generalize to more general categories. So these images quality results shows that even for some of the objects, they don't make too much sound, but still you can detect them. And if you check the paper, they have quantitative numbers. The numbers are pretty good, I would say. And these are the reference for using the audio to discover the objects. So to summarize, I just show you, we can discover objects by using motions, by using languages, and also by using audios. And this is what we know. And what we don't know is, at least to me, because these data or these problem setting are relatively small. What happens if we scale up the training? Will that be, acting very good representation for other downstream tasks? I don't know, seriously. And the second thing is, what granularity can we do? Because usually for these self-supervised object discovery, it's discover the whole object. Can we do more fine-grained, like body parts or different facial parts, etc.? And the third thing is, we know the generative model, like diffusion models, they are becoming very good. And at some point, we think they really understand the images because they can generate, the shadows, or they can generate geometry or these kind of things. But to what extent the segmentation has been built in? Because if we think they really understand the image, they must have the segmentation built in the model, right? And that's it. I think that's for my talk. Thank you for listening. Any questions?
So we already have one question in the room. Go for it.
Hi, Weidi. Thank you for the amazing talk. So my question is about the first part of the talk, about using flow. So I guess when I was, looking at the papers and playing around similar models using flow for object discovery, I find that a lot of this uses synthetic data to pre-train the flow. And often pre-training, is on data sets with only a few objects in one scene. So if you go to, let's say, a real world scene with potentially 50 or 100 actors, there's quite a large domain gap. And often when you have a lot of actors, there's actually a chicken and egg problem, because you can only do the flow very accurately if you kind of sort of already know what are the objects. So that seems to be an obvious like upper bound bottleneck for this type of flow-based object discovery. And also, the flow training part is not part of the pipeline. Once flow is trained, it's just fixed. So I'm wondering, what are your thoughts on that?
Well, my understanding is, like I said, from how human learns or these kind of things, flow really it's a starting point. You can discover the objects, but once you discover the object in the flow space, possibly you need to go back to the RGB. Let's say in the flow space, they are uniform and you discover this is the whole object. But in the RGB space, they are very different, the pixels, because people may wear, red shirt and blue, blue shoes, etc. And if you go back to the RGB space and train the model, force the model, say, you have to learn a uniform representation for all the pixels of the human, then actually you're doing something similar to supervised learning. That's exactly what supervised learning people are doing. Just you have some prior, say, these semantically they are the same, and you force the model to learn the representation to be invariant to that. So I think flow, there are several methods or several papers they are trying to do is using flow as a way to generate pseudo mask and then go back to the RGB space, distill that into the RGB space. There's a paper called DASDAB. It gets very good results. Does that answer your question?
So my point is, often the flow part learning is supervised. You need supervised learning to get the flow. And unsupervised flow, there are some unsupervised methods for the flow, but it doesn't do as good. So,
I see.
So my point is like, so you have part of the pipeline that is supervised, which is the flow part. And if you scale that to the real world scene, right, unsupervised flow is very tricky to get that to work.
I see. But I think self-supervised flow is also a progressing community, like AutoFlow, or I think Google published several flow papers this year and last year, right? All doing self-supervised. And on the Sintel, these kind of benchmark, they are doing quite well. I think similar to the Raft already.
I see. Thank you.
So I don't know if there are more questions. I actually had one. During your talk, I was wondering, what is your favorite modality to work with and why?
I think nowadays, I think language possibly is my favorite, but it's very crowded. So it's very difficult to do it with, with limited resources. But I would say language is my favorite, I think.
Okay, thanks. We have another one in the room.
Thank you very much for the talk. I just had a quick question about the first techniques using flow. The thing is, like, when you are trying to segment objects using the flow, you face the problem is like, because we get articulated motion, we get to over segment the objects. I'm working in this field, and and I don't know if you have any idea like we could do to like avoid this over segmentation, because as long as we as long as we segment with motion, we always get articulated motion all the way. And so I don't know if you have any like ways we could face it, or.
Well, it's hard to say it's a good thing or bad thing, actually, because like I mentioned in the last slides, which granularity we are talking about. If you talk about the whole human, the whole person, maybe articulate is not great. But if we're talking about want to segment the person into limbs or body, it's a good thing, right?
Yeah, for sure. But the best thing is control. It's like if you could choose to do it, because most of the techniques, for example, probable motion pattern, are using flow to segment, and then are using Dino features to group the segments together. And that's that's kind of a trick that is kind of hidden in some way, because like we don't like, but I don't know if there's like any signal we could use outside of the features or outside of pre-trained features to group the motion together. Like
yeah, I think ideally we want something like some different hierarchy of the segments.
Yeah.
It's really proposals. You can pick, you can maybe use in context learning later on to pick which hierarchy you really are interested in.
yeah. Okay. Well, thank you very much. It was very nice.
I had another question. I was wondering in the video with the video modality, so you're able to find object that move, sorry. And I was wondering, what about the other ones, the object that do not move, and if you have thoughts on that. I guess if the camera is moving, maybe there is some idea there. Yeah.
Well, first thing is, if the object doesn't move along the whole video, relying on motion, we can't do anything. But what we defined the problem before is, if the object moves in any of the frame and we want to get it out, get it segmented. And if that's the case, say the object never moves, then maybe depth can give you other information, because as long as it's not panning, you use the camera just walking around, the depth map could possibly be used similarly as the flow map.
Mm-hmm. Okay, thanks. Any more question in the room? Online? So thanks a lot, Weidi, for your great talk and for the question answering, I guess.